Good evening and welcome to Physic for Sleep. Tonight we embark on an intellectual journey exploring what lies beyond the universe, theories on the multiverse and the void. Before we gently immerse ourselves in these boundless possibilities, I would like to know where you are at this moment. Perhaps you are listening from a quiet window seat as rain gently taps against the glass. Or maybe you are comfortably nestled in your bed, gazing at the ceiling. If these deep reflections help you relax and organize your thoughts before sleep, please support the channel with a like and subscribe so others can find their way here too. Now, just breathe, allow your eyes to grow heavy, and let's begin. We often speak of the universe as if it were a singular enclosed entity, a complete cosmic sphere, easily defined and contained. But the truth, as modern cosmology reveals, is far more nuanced and perhaps more profoundly expansive. Our current understanding begins not with the entirety of existence, but with what we call the observable universe. This is not the whole cosmos, but rather the immense portion of it from which light or any other electromagnetic radiation has had enough time to reach us since the Big Bang. Imagine, if you will, a vast luminous bubble with our planet, our solar system, indeed our galaxy, situated somewhere near its center, a unique vantage point from which we perceive the cosmos. Its radius extends approximately 46.5 billion light-years in every conceivable direction, defining a sphere of cosmic history rather than merely a spatial boundary. Within this immense volume, we can detect the shimmering points of distant galaxies, each an island of hundreds of billions of stars, separated by unimaginable voids. We can trace the faint afterglow of creation itself, the cosmic microwave background radiation, a primordial light that echoes from a time when the universe was less than 400,000 years old. This observable sphere represents the sum total of our direct sensory and instrumental experience of existence, a breathtaking expanse filled with perhaps 2 trillion galaxies. Yet, even as we gaze upon this grand tapestry of light and matter, a fundamental question arises, inviting us to look beyond. What truly lies beyond the perceived edges of this observable realm? Is it simply more of the same? Stretching out endlessly, a continuous and homogeneous cosmic ocean? Or is there something fundamentally different, something that entirely defies our current understanding of space and time, perhaps even of reality itself? The boundary of our observable universe, it is crucial to understand, is not a physical wall or a cosmic barrier, but a horizon of information. It is a limit imposed by the finite speed of light and the finite age of the cosmos. Light from objects that are beyond this horizon simply hasn't had enough time to travel across the vast distances of expanding space-time to reach our telescopes and instruments here on Earth. So, while we cannot see or directly interact with anything beyond this cosmic light cone, scientists overwhelmingly believe that the universe extends far, far beyond this visible bubble. The question then naturally becomes, how far does it truly go? Is it ultimately finite, like the surface of a sphere, as we might visualize the Earth's surface, where if you travel in one direction long enough, you eventually return to your starting point, yet never encounter a distinct edge? Or is it truly infinite, stretching out without end, a boundless expanse of space, matter, and energy, a never-ending cosmic tapestry? Current data, particularly from meticulous measurements of the cosmic microwave background radiation, suggests that the large-scale geometry of the universe is remarkably flat. This flatness is not a statement about a two-dimensional plane, but rather about the curvature of three-dimensional space within a four-dimensional space-time. This observed flatness implies that the universe is either geometrically infinite in extent, or so incredibly vast that its curvature is beyond our current ability to detect, much like standing on a seemingly flat beach and being unable to perceive the subtle curve of the Earth beneath your feet. If the universe is indeed infinite, then the very concept of beyond transforms. It ceases to be a qualitative difference, a realm of entirely new physics or dimensions, and becomes merely a quantitative one. More space, more galaxies, more clusters, more of everything, forever unfolding in a statistically uniform manner. This profound idea of an infinite universe carries with it an almost unsettling, yet deeply logical, implication. If space is truly boundless and contains a finite, albeit enormous, amount of matter and energy distributed across it, then eventually patterns must repeat. Consider this thought experiment. Within any finite volume of space, there are only a finite number of ways that particles can be arranged. If you then imagine an infinite volume, a truly endless expanse, then every possible configuration of particles, every possible event, every possible you or me with your unique set of memories and experiences must eventually occur, not just once, but an infinite number of times, in an infinite number of spatially separated regions. This isn't merely a philosophical musing or a fanciful notion, but a direct consequence of the laws of statistical mechanics when applied to an infinite, homogeneous, and isotropic universe. A universe that looks roughly the same in all directions and at all locations on grand scales. Far beyond our observable horizon, in regions we can never hope to reach or even glimpse, there could be other Earths, other solar systems, other galaxies, entirely identical to our own, down to the minutest quantum detail. In fact, if the universe is infinite, there would be an infinite number of them. And in some of these infinitely distant duplicates, perhaps a version of you is listening to a strikingly similar lecture, pondering the very same profound questions about existence and cosmic scale. The very uniqueness we often attribute to ourselves, to our planet, to our precious moments in time, dissolves into an infinite tapestry of recurrence. However, the idea of beyond can also take on a different, arguably even more radical form, moving beyond the mere spatial extent of our universe to the concept of entirely separate universes, a multiverse. This is not simply more space filled with more galaxies. It refers to entirely distinct realms, perhaps governed by different fundamental physical laws, born from different cosmic origins. One of the most compelling theoretical frameworks for a multiverse arises from the theory of cosmic inflation. Just fractions of a second after the Big Bang, our nascent universe underwent an incredibly rapid exponential expansion, stretching space itself faster than the speed of light. This burst of inflation smoothed out space-time, flattened its geometry, and laid the groundwork for the large-scale structure we observe today, seeding the universe with the tiny quantum fluctuations that would later grow into galaxies and clusters. However, some advanced models of inflation, such as eternal inflation, suggest that this inflationary process may not have stopped everywhere simultaneously. Instead, inflation might be an ongoing, continuous process, perpetually generating new bubble universes in a vast, overarching space-time, much like an endlessly boiling pot of cosmic foam. Our universe, in this view, would simply be one such bubble, a pocket where inflation has locally ended, allowing for the conditions necessary for the formation of stars, galaxies, and ultimately, life. Outside our bubble, in the larger multiverse or meta-universe, inflation continues relentlessly, constantly spawning new realities, each potentially unique. These other universes, if they truly exist within this framework, would be causally disconnected from our own. Light or any form of information from them could never reach us, as they are not merely distant in space within our universe, but fundamentally separated from us by regions of intensely and rapidly inflating space-time. Each bubble universe could, in principle, have its own unique set of fundamental constants, its own specific particle masses, and its own distinct physical laws. Imagine, if you will, a universe where gravity is not an attractive force, but a repulsive one, pushing objects apart rather than drawing them together. Or a universe where light travels at a vastly different speed, altering the very nature of interaction. Perhaps a realm where the fundamental forces are tuned such that the very atoms that make us up cannot form. Or where life as we know it is utterly impossible. These are not just fanciful ideas from science fiction. They are mathematical possibilities within certain inflationary models, where the landscape of parameters can vary from one bubble to the next. Another deeply intriguing concept related to the multiverse is the many worlds interpretation of quantum mechanics. This suggests that every time a quantum event occurs, every time a particle's state is measured or observed, the universe, in a sense, splits into multiple branches, with each branch representing a different possible outcome. In this view, all possibilities are realized, not just the single outcome that we happen to observe in our particular branch of reality. So, if you made a choice today, in another universe, a version of you made a different choice. This isn't about distant bubbles in space. It is about an ever-branching tree of realities, continuously spawning new timelines with every quantum flicker, every random event, every roll of the cosmic dice. Such deeply theoretical concepts like the many worlds interpretation invite us to consider that reality might be far more layered and complex than our everyday experiences suggest. But the idea of a multiverse extends beyond these branching quantum possibilities. Another fascinating avenue of thought, born from string theory and its more encompassing successor, M-theory, proposes that our universe might not be the only one, nor necessarily the deepest layer of reality. Instead, it could be a brain, a kind of cosmic membrane, floating within a higher dimensional space often referred to as the bulk. Imagine, for a moment, fish swimming within a vast, boundless ocean. To these fish, their reality is fundamentally two-dimensional. They perceive only length and width, unaware of the third dimension of height that surrounds them. They live on a surface, within a volume, but their senses are confined to that surface. In a similar vein, our universe, with its three spatial dimensions and one of time, could be a three-dimensional brain embedded within a much larger, unseen, higher dimensional space. The particles and forces that constitute our everyday reality, the light that allows us to see, the strong and weak nuclear forces that bind atoms, might be inherently tied to this brain, unable to escape into the extra dimensions. However, gravity, that most pervasive and mysterious of forces, might be an exception. Some theories suggest that gravity, unlike other forces, could leak out into these higher dimensions, spreading its influence across the bulk. This leakage could explain why gravity appears so much weaker than the other fundamental forces within our observable universe. The vastness of the bulk, absorbing some of its strength, would dilute its apparent power to us, much like a distant sound fading with distance. This brain world hypothesis opens up a truly profound vision of the cosmos. It suggests that other brains, other universes, could exist very close to our own, perhaps separated by only a microscopic distance in a higher dimension, yet utterly invisible and inaccessible to us. These neighboring brains could be entirely different, with their own unique sets of physical laws, their own fundamental particles, perhaps even different numbers of spatial dimensions. The Big Bang itself, the momentous origin of our universe, could, in this scenario, be reimagined not as an absolute beginning from nothing, but as a violent collision between two such brains. Picture two immense flexible membranes drifting through the higher dimensional bulk, eventually brushing against each other or even smashing together. The immense energy released in such a cosmic impact could have sparked the rapid expansion and creation of matter that we identify as the Big Bang in our own three-dimensional reality. This would mean that the before the Big Bang wasn't empty nothingness, but rather a pre-existing higher dimensional space containing other brains, other universes, engaged in their own cosmic dance. The implications of such a model are staggering. It suggests that our universe is not isolated, but part of an immense, perhaps infinite, cosmic tapestry woven from countless brains. These other universes might be teeming with different forms of life, or they might be barren, devoid of structure, depending on the specific physical laws that govern them. We are, in this view, not merely residents of a vast universe, but inhabitants of a single membrane within an even grander, more expansive and intricate architecture. The questions we ask about what lies beyond our universe then transform. It is no longer just about the spatial extent of our own cosmic bubble, but about the very nature of existence itself, about the possibility of other forms of reality that exist alongside or embedded within our own, just beyond the reach of our current senses and instruments. It nudges us to consider that our perception of everything might be fundamentally limited by our three-dimensional perspective, much like the fish in the ocean, confined to their surface world, could never truly grasp the boundless volume of water that surrounds them. This journey into the multiverse inevitably leads us to an even more fundamental query. If there are multiple universes, or if our universe is a brain, what lies beyond that? What is the ultimate void or nothingness from which all these possibilities might emerge, or within which they are contained? For a long time, the concept of nothing was taken as a simple absence of everything. No matter, no energy, no space, no time. But in modern physics, the vacuum, the seemingly empty space, is anything but empty. As we discussed in a previous reflection, the quantum vacuum is a seething foam of virtual particles constantly popping in and out of existence, a restless energetic field. So, the void we speak of now when contemplating the origin of universes must be even more profound than this quantum foam. It must be a state prior to or outside of space-time and its inherent quantum fields. Scientists grapple with this concept, seeking to understand if the universe could truly arise from a state of nothing in the most absolute sense, or if there must always be some underlying framework, some pre-existent set of laws or principles from which reality can spontaneously manifest. Some theoretical physicists exploring the frontiers of quantum gravity have proposed models where space-time itself is not a fundamental, immutable backdrop, but an emergent property. Just as temperature emerges from the collective motion of countless atoms, so too might space and time emerge from a more fundamental, pre-geometric state. In such a scenario, the void might not be an empty container, but rather a realm of pure potential, a mathematical possibility space where the very laws of physics are waiting to be realized. Stephen Hawking, for instance, in his no-boundary proposal, suggested that the universe might not have had a distinct beginning in time, but rather that space-time smoothly emerged from a state akin to the South Pole on Earth, a point from which all directions lead north, but beyond which there is no further south. This avoids the thorny question of what came before by positing a universe that simply is, without needing an external cause or an antecedent state of absolute nothingness. It's a universe that is self-contained, a closed system in a very profound sense, where even its origin is encoded within its own mathematical structure. This contemplation shifts our perspective from merely observing the universe to recognizing its profound mystery, its capacity to arise from conditions that defy our intuitive understanding. The ultimate void in this context is not a barren emptiness, but an enigmatic realm of latent laws and unrealized possibilities, a silent matrix from which the symphony of existence, in all its multitudinous forms, could emerge. And as we consider these grand, almost unimaginable scales and origins, we are reminded of our own fragile yet remarkable existence within this cosmic unfolding. Our consciousness, our ability to ponder these very questions, is a testament to the universe's capacity for self-awareness. A brief, luminous pattern woven into the grand fabric of space-time, allowing us to glimpse the profound depths of reality, even as we drift into the tranquil expanse of sleep. This contemplation that our universe might be but one bubble or brain among many, naturally leads us to ponder the remarkable conditions within our own cosmic home. Why are the fundamental constants of physics, the very rules that govern matter and energy, so exquisitely tuned to allow for the existence of stars, galaxies, and ultimately life itself? This is the essence of the fine-tuning problem, a profound puzzle that has captivated scientists and philosophers alike. It suggests that if certain values, such as the strength of the electromagnetic force, the gravitational constant, or the mass of elementary particles were even fractionally different, the universe we know simply would not exist. Consider, for instance, the delicate balance of the strong nuclear force which binds protons and neutrons together within atomic nuclei. If it were just slightly weaker, stable atoms heavier than hydrogen could not form, leaving a universe devoid of the rich chemistry necessary for complex structures. If it were slightly stronger, hydrogen itself would have fused too quickly in the early universe, leaving no fuel for long-lived stars like our Sun. Or think of the cosmological constant, the elusive dark energy that drives the accelerating expansion of the universe. Its observed value is incredibly small, but if it were even a tiny bit larger, the universe would have expanded so rapidly that matter would never have had a chance to clump together under gravity to form galaxies and stars. Conversely, if it were much smaller or even negative, the universe might have collapsed back in on itself long ago, never reaching a state where life could emerge. Such exquisite fine-tuning seems almost miraculous, leading some to invoke an intelligent designer while others seek a scientific explanation. The multiverse hypothesis, particularly the eternal inflation model we touched upon, offers a compelling, albeit untestable, solution. If there are indeed an infinite number of universes, each with slightly different physical laws and fundamental constants, then it stands to reason that at least one of them, purely by chance, would possess the precise conditions necessary for the emergence of complexity and consciousness. Our existence, then, would not be a miracle in a single universe, but an inevitable outcome within a vast ensemble of realities. We simply find ourselves in the universe where the dice happen to roll in our favor because we could not exist in any other. This is known as the anthropic principle, the idea that the universe must be compatible with the existence of intelligent life, because intelligent life is observing it. It's a subtle shift in perspective, transforming a seemingly improbable cosmic coincidence into a statistical certainty across an infinite landscape of possibilities. This idea that our existence is tied to specific cosmic parameters invites us to reflect on the transient nature of our own moment within the universe's grand narrative. It's a reminder that the stability and predictability we experience are not universal constants, but rather a localized, temporary equilibrium. And as we consider the potential for infinite variations, we might also ponder if the universe itself, or perhaps the larger multiverse, operates in cycles, endlessly repeating its cosmic dance. This brings us to another fascinating theoretical concept, the cyclic universe, sometimes known as the Big Bounce. The prevailing cosmological model, the Big Bang, describes the universe originating from an incredibly hot, dense state approximately 13.8 billion years ago, and expanding ever since. But what if this was not the absolute beginning? What if our Big Bang was merely a rebound from a previous universe that had contracted to an incredibly dense state? The Big Bounce theory proposes that the universe undergoes an endless succession of expansions and contractions, each cycle beginning with a bounce from a previous collapse. Instead of a singularity, a point of infinite density where physics breaks down, the universe reaches a minimal size and then rebounds, smoothly transitioning from contraction to expansion. This avoids the problematic singularity of the traditional Big Bang model and offers a continuous, eternal narrative for the cosmos. In this view, what lies beyond the universe is not a spatial void, but rather an endless temporal sequence of prior universes, each evolving, expanding, and then contracting, only to give birth to the next. The Big Bounce model posits a universe that is truly eternal, not in its current expanding form, but in its cyclical nature. Each iteration might be slightly different, perhaps with variations in physical constants or initial conditions, allowing for an evolutionary process across cosmic epochs. Our current universe, with its specific laws and structures, would then be one particular manifestation within this grand recurring cycle. This offers a profound sense of continuity, where destruction and creation are not opposing forces, but two inseparable phases of an eternal cosmic rhythm. It suggests that the matter and energy that compose us, the very space-time we inhabit, have perhaps existed through countless cycles, endlessly transforming and reforming across unimaginable spans of time. The atoms in your body, the light in your eyes, the thoughts in your mind, they might be ancient echoes of previous cosmic epochs, having participated in the birth and death of universes stretching back into an infinite past. It's a humbling thought, connecting our ephemeral existence to the deep, resonant pulse of an eternal cosmos, allowing us to find peace in the cyclical nature of all things, even as our own awareness fades into the quiet embrace of sleep. The concept of a cyclic universe where existence perpetually renews itself through cosmic bounces offers a compelling vision of eternity, a rhythm of creation and destruction stretching into an infinite past and future. But this notion of cosmic recycling brings with it another profound puzzle, one that lies at the very heart of how we understand the fundamental nature of reality itself: the information paradox. In quantum mechanics, a cornerstone of modern physics, information is never truly lost. It can be scrambled, transformed, or hidden, but it cannot simply vanish from existence. This principle, known as unitarity, is deeply ingrained in the quantum laws governing the universe. Yet, when we consider black holes, these enigmatic cosmic entities, they present a formidable challenge to this fundamental tenet. When matter falls into a black hole, it crosses the event horizon, the point of no return, and is seemingly swallowed into a singularity, a point of infinite density. From an outside perspective, the information about that matter appears to be utterly destroyed, lost forever behind the veil of the horizon. This apparent destruction of information contradicts the very foundations of quantum theory. Scientists have grappled with this paradox for decades, with profound implications for our understanding of reality and what lies beyond the event horizon, and perhaps, by extension, beyond our universe. One of the most intriguing proposals to resolve this paradox emerged from the work of physicists like Jacob Bekenstein and Stephen Hawking, and later expanded by Gerard 't Hooft and Leonard Susskind: the holographic principle. This principle suggests that all the information contained within a three-dimensional volume of space, such as the matter that falls into a black hole, might actually be encoded on a two-dimensional surface that bounds that volume. Think of it like a hologram. A three-dimensional image is projected from information stored on a flat, two-dimensional plate. In the context of black holes, the information about everything that falls in is not lost, but rather imprinted onto the two-dimensional surface of its event horizon. This isn't just a clever trick. It's a deep mathematical insight that implies a profound connection between different dimensions of reality. If this is true for black holes, then it begs a larger question. Could our entire three-dimensional universe, with all its galaxies, stars, planets, and even ourselves, be a holographic projection from a much more fundamental, two-dimensional informational surface that exists beyond our perceived reality? This idea that our familiar three-dimensional world is in some sense emergent from a two-dimensional boundary profoundly redefines what beyond the universe could mean. It suggests that the ultimate reality might not be a vast, sprawling cosmos in four dimensions of space-time, but rather a flat, informational layer, a canvas upon which our perceived reality is painted. We would, in essence, be living within a cosmic hologram. This isn't to say our reality is fake or an illusion in the common sense, but rather that its deepest, most fundamental description might reside in a lower dimensional form, much like a complex computer program can generate a rich, interactive three-dimensional world from lines of code. The vastness we perceive, the depth we experience, the very solidity of objects could all be intricate manifestations of information encoded on a distant, unseen boundary. This perspective transforms the void from an empty space into a potential source of ultimate information, a silent, unseen substrate from which all of existence emanates. The holographic principle, though still theoretical, provides a powerful framework for thinking about the fundamental limits of information and the nature of space-time itself. It resonates with another profound, albeit speculative idea that further pushes the boundaries of what lies beyond our universe: the simulation hypothesis. This hypothesis, explored by philosophers and physicists alike, suggests that our universe and everything in it might actually be a sophisticated computer simulation run by a more advanced civilization. If we consider the rapid progress of computing power and our increasing ability to create realistic virtual worlds, it is not unreasonable to extrapolate that a sufficiently advanced civilization could one day create simulations indistinguishable from reality for their inhabitants. If such simulations are possible, and if there are many advanced civilizations, then statistically it is more likely that we are living in a simulation than in the base reality. In this context, beyond the universe would refer to the higher-level reality of the simulators, the computational substrate upon which our universe runs. It would be a realm of existence whose physical laws, technologies, and consciousness might be entirely alien to our own, yet they would be the ultimate architects of our perceived cosmos. This idea, while unsettling to some, can also be a source of profound wonder. It recasts our universe not as an accidental byproduct of random processes, but as a meticulously designed, albeit artificial, creation. Our quest to understand the universe would then be a quest to understand the code and algorithms that define it, and perhaps to glimpse the nature of its creators. It invites us to consider that the very fabric of existence, the laws of physics that we diligently uncover, are themselves reflections of a deeper computational architecture. And when we consider the elegance of mathematical laws, the surprising effectiveness of mathematics in describing nature, this hypothesis gains a subtle, quiet resonance. Whether our universe is a holographic projection, a cycle in an eternal bounce, or a meticulously crafted simulation, these theories all invite us to transcend our immediate perceptions and ponder the deeper, hidden layers of reality. They challenge our intuitive understanding of space, time, and existence, transforming the void from a simple absence into a realm of immense potential, a canvas upon which realities are painted, or a computational engine where universes are born. And as we drift with these thoughts, we might find a quiet calm in the realization that our individual consciousness, our fleeting moment of awareness, is part of a grander, more intricate cosmic design, a profound mystery unfolding in the silence of the night. If our reality is indeed a holographic projection or a sophisticated simulation, then the profound question of what lies beyond the universe transforms from a spatial or temporal query into one about the very nature of its underlying substrate. It moves us to consider not just more of our universe or other universes, but the fundamental realm from which all these possibilities might emerge. This takes us to the deepest conceptual void, a state of nothingness far more abstract than the quantum vacuum teeming with virtual particles that we discussed earlier. This is a void prior to space-time, prior to physical laws, prior to even the potential for particles or fields. How can something, let alone everything, arise from such an absolute absence? This question has long been a philosophical cornerstone, but modern physics, particularly at the intersection of cosmology and quantum gravity, offers intriguing, albeit speculative, avenues for exploration. One such avenue delves into the idea that perhaps the universe, or the multiverse, is fundamentally a mathematical structure. This mathematical universe hypothesis, championed by cosmologist Max Tegmark, suggests that our physical reality is not just described by mathematics, but is mathematics. In this view, the universe is not merely governed by mathematical laws. It is itself a mathematical entity, existing independently of any human observation or physical substrate. If this is true, then what lies beyond our universe could be the vast, abstract realm of all possible mathematical structures. an infinite landscape of potential realities. Our universe would be just one particular, self-consistent mathematical structure that is complex enough to contain observers capable of contemplating its nature. This would imply that every conceivable mathematical structure that could exist exists in some form as a universe. It's a breathtaking thought, suggesting an ultimate void that isn't empty, but rather a plenum of pure abstract mathematical forms, each capable of spawning a unique physical reality. Within this abstract framework, the very idea of a physical universe becomes a derived concept, an emergent property of underlying mathematical relationships. The laws of physics, the fundamental constants, the dimensions of space-time, all would be inherent features of a specific mathematical structure. This shifts our understanding of creation from a physical event to a mathematical realization. It implies that the deepest reality is not material, but abstract, an eternal and unchanging tapestry of numbers and relationships. And when we consider the profound effectiveness of mathematics in describing the cosmos, the way that elegant equations can predict phenomena from the smallest particles to the largest galaxies, this hypothesis gains a quiet, intellectual resonance. It offers a sense of profound order, even in the face of infinite possibilities, suggesting that the universe is not a chaotic accident, but a coherent, logical expression of an underlying mathematical truth. Our own thoughts, our ability to comprehend these mathematical ideas, might then be seen as a small, conscious part of this self-aware mathematical structure, a reflection of its inherent logic. But how do these abstract mathematical structures become the concrete, vibrant reality we experience? This is where the concept of consciousness might play an unexpectedly central role. While most physicists would argue that consciousness is an emergent property of complex brains within a pre-existing physical universe, some radical theories explore the possibility that consciousness itself is fundamental, or that it plays a crucial role in shaping reality. This takes us to the most speculative edge of what lies beyond, touching upon the very boundary between the objective physical world and subjective experience. Could the act of observation, the presence of consciousness, somehow select or actualize one particular mathematical structure out of the infinite possibilities, giving rise to our specific universe? This echoes the many worlds interpretation of quantum mechanics, where every quantum choice leads to a branching reality, but elevates consciousness to a more active role in this branching process. In this deeply contemplative view, the ultimate void might not be a place or a state, but rather a boundless sea of pure consciousness or proto-consciousness, a fundamental awareness from which all universes and all experiences emerge. This is a concept explored in various philosophical traditions, but it finds a tangential, albeit highly speculative, echo in some interpretations of quantum theory, where the observer seems intrinsically linked to the collapse of the wave function, forcing a probabilistic quantum realm into definite classical outcomes. If consciousness is indeed fundamental, then beyond the universe could be the infinite, undivided field of awareness that gives rise to all possible realities, including our own. Our individual minds would then be like ripples on this vast ocean, momentary manifestations of a deeper, universal consciousness, experiencing a particular slice of reality. Such ideas, while pushing the very limits of empirical science, offer a profound sense of interconnectedness. They suggest that our place in the universe is not one of detached observation, but of intrinsic participation in its unfolding. Whether we are living in an infinite expanse, a holographic projection, a cosmic simulation, a cyclic rebirth, or a manifestation of mathematical truth, our existence is inextricably linked to the grand overarching reality. The unknown beyond ceases to be a frightening emptiness and becomes a canvas of infinite potential, a source of endless wonder. And as these thoughts gently settle in your mind, allowing the immensity of these possibilities to wash over you, you might find a tranquil sense of belonging within the vast, mysterious tapestry of existence. a quiet understanding that even in sleep you remain a part of this grand, unfolding cosmic drama. The profound implications of a universe potentially rooted in mathematical structures or even influenced by consciousness, as we have just contemplated, inevitably lead us to a further, equally significant realization. Our understanding of what is inextricably bound by the inherent limitations of our perception. We construct our reality through the intricate filters of our senses and the sophisticated tools of our science, which, while remarkably powerful and ever advancing, are nevertheless constrained by the very framework of our existence. This begs a crucial question. What if there are aspects of beyond the universe that are not merely distant in space or remote in time, but are fundamentally inaccessible to our current modes of sensing, our established scientific instruments, or even the logical frameworks of our intellect? Our perception is, after all, a delicate product of evolution within this particular universe, meticulously adapted to its specific physical conditions and energy scales. Could there be phenomena, dimensions, or even entire realities that simply do not register within our biological or technological capacity, existing in a state of perpetual, profound unknowability? This idea invites a deep humility, reminding us that the vast tapestry of existence might contain colors we cannot see, frequencies we cannot detect, and forms we cannot conceive. Not because they are not there, but because our sensory and cognitive apparatus is simply not equipped to register them, much like a radio tuned to one frequency remains unaware of the myriad other broadcasts filling the airwaves. Imagine for a moment a hypothetical creature whose entire existence is confined to the surface of a two-dimensional plane, a being perceiving only length and width. Its reality would be fundamentally flat. The concept of up or down beyond its surface would be utterly alien, an abstract impossibility, perhaps even a contradiction in terms within its limited experience. Such a creature, if it were capable of scientific inquiry, would develop a system of physics entirely suited to its flat world, with laws governing interactions only along two axes. Now, if a three-dimensional object, let us say a perfect sphere, were to pass through its plane, this two-dimensional creature would only perceive a changing cross-section, a dot appearing, gradually growing into a perfect circle, then steadily shrinking and finally vanishing, never truly comprehending the full volumetric nature of the sphere itself. It would observe effects, a sequence of expanding and contracting circles, but never the actual cause in its full dimensionality. In a remarkably similar vein, our universe, with its three familiar spatial dimensions and one of time, could itself, as suggested by some advanced theories like those found in string theory and M-theory. We are, in this analogy, the two-dimensional beings, experiencing only a particular slice or projection of a richer, more expansive reality. Our perceived universe, then, is merely a shadow cast by a higher dimensional truth, a limited view whose full, intricate form remains beyond our current grasp. This intriguing idea, far from being a mere philosophical flight of fancy, emerges directly from the rigorous mathematics of these cutting-edge theories, providing a potential solution to some of the most stubborn problems in physics. To maintain their internal consistency and provide a unified description of all fundamental forces of nature, often necessitate the existence of additional spatial dimensions, typically 10 or 11 in total. These extra dimensions are frequently theorized to be compactified or curled up into incredibly tiny, subatomic spaces at every single point in our familiar three dimensions, making them imperceptible to our current methods of observation. They are like infinitely small, intricate knots woven into the very fabric of space-time, affecting phenomena at the quantum level, but remaining macroscopically hidden from our view. Much like the intricate details of a tapestry are lost when viewed from a great distance. However, another, even more radical possibility exists within these models. What if some of these dimensions are not curled up at all, but simply exist in a large or extended form, yet remain beyond our ability to directly interact with them? Or perhaps They host entirely different forms of matter and energy that do not interact with our own in any detectable way, except possibly through the subtle, elusive influence of gravity, which some models suggest could leak into these higher dimensions, thereby explaining its comparative weakness relative to other fundamental forces in our universe. This would mean that beyond the universe is not a distant, empty void, but an intricate, interwoven layer of reality, coexisting with us in the same location within the greater bulk space-time, yet remaining profoundly hidden within a grander cosmic architecture, a silent, parallel existence just out of reach, shaping our reality in ways we are only beginning to theorize. The implications of such hidden dimensions and alternative forms of reality further transform our understanding of the ultimate void. If reality itself is ultimately a self-contained mathematical construct, as Max Tegmark suggests, or if consciousness plays a foundational role in its manifestation, then the ultimate nothingness ceases to be a simple, empty container or a passive backdrop. Instead, it becomes a state that precedes even mathematical definition, a realm where even the most fundamental axioms are not yet established, a blank slate before the rules are written. Or, if consciousness is truly primary, the void might be an infinite sea, utterly devoid of even the most nascent forms of awareness, a pure, unmanifest potential, a silent dream before any thoughts are formed. It represents a conceptual frontier that challenges the very limits of our language, our logical frameworks, and our intuitive grasp of existence, pushing us to the edge of what can be articulated or even imagined. To truly comprehend such a void would be to transcend the very categories of thought we employ to make sense of the world, categories like space, time, cause, and effect, for these would be the creations from the void, not properties, of Hyo, it. It suggests a pre-cosmic state that is not merely dark and silent, but utterly without attributes, without inherent potential, a true absolute absence from which, paradoxically, the rich tapestry of existence itself might have spontaneously emerged, a profound mystery at the very heart of all that is. This resonates deeply with ancient philosophical meditations on the primordial ground of being, but recontextualizes them within the rigorous, albeit speculative, language of modern theoretical physics, offering a new, breathtaking lens through which to view the genesis of all things and the nature of non-existence, a quiet invitation to embrace the unknown. This deeply profound exploration into the nature of reality and the ultimate void ultimately brings us back to ourselves, to the unique and remarkable position of human consciousness within this grand cosmic mystery. We are, in a very real and astonishing sense, the universe reflecting upon itself, the cosmos becoming aware of its own intricate existence and its own profound unanswered questions. Our individual thoughts, our relentless inquiries, our very capacity for wonder and contemplation are not separate from this larger cosmic unfolding, but are, in fact, an intricate and essential part of it. The search for what lies beyond the universe is, in many ways, a deeply personal search for the deepest truths. A quest constrained by the very nature of our perception. Our senses and scientific instruments, while powerful, operate within a specific set of physical laws and energy scales. This leads to a fascinating and perhaps slightly unsettling thought. What if the ultimate void, or the larger meta-reality, is not just a passive emptiness, but a dynamic entity with hidden properties, capable of changing its fundamental state in ways that could redefine existence itself? And to consider the subtle shifts of cosmic possibility. This invitation to embrace the unknown is perhaps most keenly felt when we confront the profound challenge of verifying these grand theories of the multiverse and the ultimate void. How, after all, can we prove the existence of realms that are, by their very definition, beyond our observable universe, causally disconnected, or existing in dimensions entirely imperceptible to us? The very nature of scientific inquiry relies on observation, experimentation, and the ability to gather empirical evidence. Yet, for many of these concepts, Such direct verification seems an impossibility, pushing the boundaries of what we traditionally consider science. This doesn't render these ideas invalid. Rather, it highlights the current limits of our tools and methodologies, forcing us to rely on theoretical consistency, mathematical elegance, and indirect clues. Consider the theories of eternal inflation or the brain world. While they offer compelling solutions to puzzles like cosmic fine-tuning or the weakness of gravity, their predictions often manifest as statistical probabilities across an ensemble of universes, or as subtle imprints on our own cosmic microwave background radiation that are incredibly difficult to distinguish from other phenomena. The signals, if they exist, are often too faint, too nuanced, or too deeply embedded in the noise of other cosmic processes for our present-day instruments to definitively isolate. It is akin to trying to discern the exact pattern of a single raindrop in a vast, tumultuous ocean during a storm. Scientists like Alan Guth and Andre Linde, pioneers in inflationary cosmology, continue to develop models that might yield testable predictions, even if those tests are indirect. They search for peculiar signatures in the primordial universe that could only arise from interactions with other inflating bubbles or from the dynamics of extra dimensions. But these are exceedingly subtle whispers from the edge of existence, requiring generations of technological advancement and theoretical refinement to potentially decipher. The current state of affairs means that while the multiverse offers elegant explanations, it remains largely within the realm of theoretical physics, a landscape of profound conceptual beauty awaiting the dawn of definitive evidence. This challenge of verification extends even more profoundly to the concept of the ultimate void, a state preceding space, time, and physical laws. How can we ever hope to observe or measure something that is, by definition, an absence of observable properties? The very act of measurement implies an interaction, a causal connection, which would inherently bring that nothingness into a state of something. This paradox underscores a fundamental limit to our empirical approach. Philosophers have long debated whether absolute nothingness is even a coherent concept, substratum, some irreducible potential from which existence can spring. If the universe is a mathematical structure, as the mathematical universe hypothesis suggests, then the void might be the realm of uninstantiated mathematical possibilities, a vast library of equations that simply exist in an abstract sense until a particular set of conditions allows one to manifest as a physical reality. In this context, the void is not empty, but full of dormant potential, a silent symphony of possibilities waiting for the right conditions to play out. The notion that consciousness might play a fundamental role in shaping reality, or even in its emergence from this ultimate void, introduces yet another layer of complexity to the problem of verification. If, as some highly speculative theories suggest, the act of observation or the presence of consciousness is necessary to actualize reality from a quantum superposition of possibilities, then how could we ever objectively study the pre-conscious state? Our very act of inquiry would, by its nature, influence the outcome. This brings us to the famous hard problem of consciousness. How do subjective experiences arise from objective physical processes? If consciousness is not merely an emergent property of complex brains, but a fundamental aspect of reality, then its role in the universe's origin and its connection to the ultimate void become far more central and enigmatic. It implies a universe that is not merely observed by conscious beings, but perhaps, in some profound sense, co-created by them. This idea, while deeply challenging to the scientific method, opens up a contemplative space where the boundaries between observer and observed, between mind and matter, begin to blur, inviting a sense of profound unity and participation in the cosmic dance. Ultimately, these theories about what lies beyond our universe, whether it's an infinite expanse of repeating realities, other brains in higher dimensions, a cyclic cosmos, a holographic projection, a mathematical structure, or a realm shaped by fundamental consciousness, are not just intellectual exercises. They are profound meditations on our place in existence. They compel us to stretch our minds beyond the familiar, to embrace the limits of our current knowledge, and to find wonder in the vastness of the unknown. They remind us that the universe is not a static, fully understood entity, but a living, evolving mystery, constantly inviting us to look deeper, to question further, and to find a quiet reverence in the immensity of what remains unrevealed. To ponder these possibilities is to connect with a fundamental human drive to understand, a drive that continues to push the frontiers of physics even into the tranquil depths of the night. The profound mystery of the ultimate void and the subtle shifts of cosmic possibility are not merely abstract intellectual exercises. They are deeply rooted in the persistent human endeavor to understand the universe through observation and careful inference. Even when direct empirical evidence seems beyond our grasp, the scientific method encourages us to seek indirect signatures, faint echoes, or unexpected anomalies that might hint at a grander reality. This quest for the unseen, for the beyond, often leads us to re-examine the very foundations of what we consider stable and immutable within our own universe. What if, for instance, the vacuum itself, the seemingly empty space that underpins our reality, is not as fixed as we perceive it to be? This brings us to one of the most intriguing and, at times, unsettling theoretical possibilities: the concept of false vacuum decay. Our universe, as modern physics understands it, resides in a particular energy state, often referred to as the Higgs vacuum. Think of it like a marble resting in a valley on a complex landscape. This valley represents a stable energy state, but it might not be the lowest possible energy state. There could be a deeper, more fundamental valley, a true vacuum, representing an even more stable configuration of reality. The universe, in this analogy, is currently in a false vacuum state, temporarily stable but susceptible to a profound, transformative shift. If a small bubble of this true vacuum were to spontaneously nucleate somewhere in our universe, perhaps through a quantum fluctuation, it would begin to expand at nearly the speed of light, converting the false vacuum into the true vacuum as it goes. This wouldn't be a violent explosion in the usual sense, but rather a slow, gentle, yet utterly fundamental alteration of the very fabric of existence. The physical laws, the properties of elementary particles, and even the nature of space and time within this expanding bubble would be fundamentally different. It would be a cosmic phase transition, a quiet reshaping of reality, turning our familiar universe into something entirely new. Such an event, though theoretical and not anticipated for billions of years, if ever, offers a powerful lens through which to consider the ultimate void. It suggests that what we perceive as the fundamental nothingness of space is, in fact, a field with an inherent energy, a fragile equilibrium that could shift. The void then becomes a dynamic entity, capable of undergoing profound transformations, hinting at a deeper, underlying metastructure that governs not just the existence of our universe, but its very stability. This concept further blurs the line between our universe and what lies beyond, suggesting that the beyond might not be spatially distant, but rather a different, more fundamental energy state, accessible through a cosmic alteration. It offers a contemplation of grand cosmic change, where our current reality is merely one transient phase within a much larger ongoing process of universal evolution. And as we consider this potential for profound cosmic transformation, we are reminded that even the most seemingly stable aspects of our reality are ultimately part of a larger, dynamic, and ever-unfolding story, a quiet dance of energy and form that invites a deep sense of wonder and calm acceptance. The implications of false vacuum decay, if it were to occur, would be absolute for our universe, yet it would not necessarily be an end in the sense of total annihilation, but rather a cosmic metamorphosis. The matter and energy that constitute our stars, galaxies, and indeed ourselves would simply cease to exist in their current forms, transforming into something entirely different, governed by new, unfamiliar laws. This concept, born from quantum field theory and the standard model of particle physics, underscores the idea that the void is not inert, but possesses inherent potential for change, a latent energy that can manifest in different forms. It moves us to think of reality as a landscape of energy states, with our universe occupying one particular peak or valley, and the beyond potentially representing other, perhaps more fundamental, landscapes. This perspective aligns with the multiverse models we discussed earlier, where different universes might correspond to different vacuum states within a larger, overarching meta-universe. Each bubble universe could be a local minimum in this cosmic energy landscape, and false vacuum decay would be the transition from a higher, less stable minimum to a lower, more stable one. This grand vision of cosmic transformation, while initially startling, can also be a source of profound tranquility. It suggests that existence itself is an ongoing process of becoming, a ceaseless dance of energy and form, where even the most fundamental properties are subject to change over immense timescales. It removes the burden of our universe being the sole, ultimate reality, and places it within a larger, more resilient framework. This doesn't diminish our existence, but rather contextualizes it within a tapestry of infinite possibilities and eternal processes. We are not just isolated observers, but participants in a cosmic drama that extends far beyond our current comprehension, a part of a reality that is richer, more intricate, and more dynamic than we could ever fully grasp. And as these thoughts gently unfold, quiet calm in the realization that your individual consciousness, your grand vision of cosmic transformation, where even the vacuum itself might undergo a phase transition, compels us to reconsider our place, not just within a single universe, but within a potentially infinite ensemble of realities. This profound shift in perspective moves us away from the comforting notion of a solitary cosmos, uniquely tailored for our existence, towards a more expansive and perhaps more humbling understanding. If our universe is but one leaf on an immense cosmic tree, as many multiverse theories suggest, then our understanding of what is becomes an ever-evolving narrative, constantly expanding to encompass realms currently beyond our direct perception or measurement. This calls for a deep intellectual flexibility and openness to the possibility that the very fabric of reality is far more intricate and diverse than our current models can fully capture. It is a journey not just into the unknown, but into the fundamentally unknowable aspects of existence, where the boundaries of science meet the frontiers of philosophy and perhaps even spirituality, inviting a quiet sense of awe. This journey into the vastness of potential realities invites us to consider the very nature of fundamental laws. If, as the eternal inflation model suggests, countless bubble universes are continually budding off, each potentially characterized by different physical constants, varying strengths of gravity, different masses for elementary particles, or even alternative numbers of spatial dimensions, then the laws of our universe are not absolute decrees for all of existence. Instead, they become localized manifestations, a specific set of rules that happen to congeal within our particular cosmic bubble, allowing for the emergence of complex chemistry, stars, and life. This concept, often termed the cosmic landscape, paints a picture of an infinite array of possible universes, each a unique solution to the underlying meta-laws of the multiverse. Our universe, with its seemingly fine-tuned parameters, is then simply one of the many viable configurations, a fortunate happenstance in a cosmic lottery. This perspective offers a powerful counter-argument to the fine-tuning problem, suggesting that our existence is not a miraculous exception, but a statistical inevitability within a sufficiently large and diverse multiverse. It means that what we consider immutable bedrock principles might merely be the local weather patterns in a much larger global climate of physics, a dynamic interplay of possibilities. The philosophical implications of this cosmic landscape are immense. It challenges our anthropocentric view, where our universe is the center of all possibility, and replaces it with a grander, more democratic vision of existence. Our unique set of physical laws, so crucial for our life, is simply one among an infinite palette of cosmic possibilities. This shifts the focus from finding a grand, singular purpose for our universe to appreciating the sheer diversity of creation. It encourages us to contemplate the vastness of potential, where every possible permutation of physical laws might be playing out in some distant, causally disconnected realm. This is not to diminish the wonder of our own universe, but to expand it, to see our reality as a precious, yet not necessarily unique, manifestation of fundamental principles. It fosters a sense of profound interconnectedness, where even seemingly disparate realities are ultimately linked by the overarching meta-laws of the multiverse, a silent, intricate web of cosmic potential, forever weaving new strands of existence. And in this immense weaving, our own consciousness, our fleeting awareness, becomes a single, intricate knot, a unique pattern within an unimaginably vast tapestry. But what of the ultimate origin, the true void from which even the multiverse itself might emerge? If the multiverse is a product of eternal inflation, then the inflationary field, the dynamic entity driving the creation of new universes, exists prior to or at a more fundamental level than individual universes. This inflationary vacuum then becomes our new void, not empty, but filled with a latent energy that continuously births new realities. Yet, even this raises the question of its own origin. This leads to the most abstract notions of a pre-geometric void, a state before space and time, before even the mathematical structures that define them. This is the realm where our scientific language struggles, where metaphors of pure potential or unmanifest consciousness often become the only means to articulate such profound absence. It is a concept that transcends empirical verification, residing purely in the realm of theoretical consistency and philosophical contemplation, a silent testament to the limits of our current understanding. This ultimate void, if such a state can be coherently defined, is not a barren emptiness, but the ground of all being, the boundless source from which all universes, all physical laws, and all consciousness might ultimately arise. It is the silence before the symphony, the canvas before the first brushstroke, the unbounded potential from which the intricate dance of existence continuously unfolds. And as we consider these profound depths, the very notion of beyond the universe becomes less about a physical boundary and more about a conceptual frontier, an invitation to recognize the inherent mystery that surrounds and permeates all that we know. It is a quiet reminder that our knowledge, however vast, is but a small island in an infinite ocean of unknowing, and in that unknowing lies the deepest sense of wonder. The contemplation of such radical theories, from holographic projections to mathematical universes and the profound void, subtly reshapes our personal relationship with reality. It invites us to consider the possibility that our own individual existence, our unique stream of consciousness, is not an isolated phenomenon, but rather a momentary, intricate pattern emerging from a much larger, more fundamental substrate. When we ponder the idea of an infinite number of universes, each with a version of ourselves, it can evoke a sense of both insignificance and profound connection. Are our choices truly our own, or are they mere echoes of decisions made in countless parallel realities? This thought, rather than leading to anxiety, can inspire a deep appreciation for the singular unfolding experience of this particular moment in this particular universe. It's a call to embrace the present, knowing that its uniqueness in some cosmic sense is simultaneously guaranteed and infinitely replicated. This paradox, a quiet hum in the background of our thoughts, allows us to find a deeper calm in the grand, multifaceted narrative of existence. This journey into the depths of cosmic theories, from the observable universe to the speculative multiverse and the abstract void, ultimately invites a profound sense of calm. It contextualizes our brief existence within an unimaginably grand and eternal narrative, where our individual experiences are fleeting yet meaningful patterns within an endless cosmic dance. To understand that our familiar universe is just one possibility among countless others, or that it might be a transient state within a larger transforming meta-reality, can alleviate the burden of seeking ultimate meaning solely within our immediate confines. It expands our horizons, not just spatially or temporally, but conceptually, creation and destruction, the constant unfolding of new forms from underlying potential. We are part of something so much larger, so much more intricate than we can ever fully grasp. And in that vastness, there is a serene comfort. The realization that our perspective is limited, that there are profound truths just beyond the reach of our senses and instruments, fosters a gentle humility. It reminds us that the universe is not obligated to conform to our expectations or to reveal all its secrets at once. Instead, it offers an endless invitation to wonder, to explore, and to contemplate. And as these deep thoughts about the multiverse and the void settle in your mind, let them carry you into a state of tranquil relaxation, a peaceful awareness of your intrinsic connection to the boundless and mysterious cosmos. The deep contemplation of our and the recognition that our universe might be but one of countless possibilities naturally leads us to question the very texture of reality at its most fundamental level. We perceive space as smooth and continuous, a vast unbroken canvas upon which the cosmic drama unfolds. Time, too, feels like an uninterrupted flow, a river carrying us from moment to moment. Yet, when we delve into the realms where the laws of quantum mechanics meet the curvature of general relativity, a different, far more intricate picture begins to emerge. This is the domain of quantum gravity, a theoretical frontier where our familiar notions of space and time may cease to apply in their conventional forms. Here, at the unimaginably tiny Planck scale, a length of approximately 1.6 times 10 to the power of minus 35 meters, and a time of around 5.4 times 10 to the power of minus 44 seconds. The very fabric of space-time is thought to dissolve into something turbulent and chaotic, a concept often referred to as space-time foam or quantum foam. Imagine the surface of a vast, tranquil ocean. From a great height, it appears as a smooth, unbroken expanse, reflecting the sky above. But as you descend closer, you begin to see ripples, then waves, and closer still, the chaotic, bubbling activity of countless individual water molecules. In a similar way, our universe appears smooth and orderly at the macroscopic scales we inhabit. However, at the extreme quantum realm, the very stuff of space and time is believed to be in a constant state of flux, bubbling and twitching with ephemeral fluctuations. These are not mere empty jitters. They represent spontaneous changes in the geometry and topology of space-time itself. Tiny fleeting wormholes might momentarily open and close, and virtual particles of space and time could pop into existence and vanish, creating a dynamic, restless substrate beneath the apparent stillness of the vacuum. John Wheeler, one of the pioneering thinkers in this field, envisioned this quantum foam as a sort of boiling, effervescent medium, a ceaseless dance of microscopic space-time curvatures. This isn't emptiness. It's a profound form of activity, a fundamental restlessness that underlies all existence, a silent, swirling chaos from which order and indeed universes might ultimately emerge. This concept of space-time foam challenges our intuitive understanding of the void. It tells us that even in the deepest nothingness imaginable, there is an inherent, unceasing quantum activity. This is not the absolute void, the pre-geometric state we previously discussed, but rather the closest approximation to empty space within the quantum gravitational framework. It is a substratum that is pregnant with potential, a latent energy that can, under certain conditions, manifest into the macroscopic universe we observe. Some theories even suggest that new universes could spontaneously bubble off from this quantum foam, like tiny self-contained Big Bangs arising from immense fluctuations in this primordial sea. Each of these nascent universes could then inflate rapidly, expanding into its own distinct reality, potentially contributing to the larger multiverse. This provides a direct physical mechanism for the continuous generation of new realities, connecting the microscopic chaos of quantum foam to the macroscopic grandeur of cosmic creation. It implies that the beyond is not just a place of other universes, but a generative process, a perpetual cosmic birthing ground. The quest to understand this quantum nature of gravity is one of the most profound challenges in modern physics. General relativity, which describes gravity as the curvature of space-time on large scales, works beautifully for stars and galaxies. Quantum mechanics, which describes the behavior of particles at the smallest scales, is incredibly successful for atoms and subatomic particles. Yet, these two pillars of modern physics are fundamentally incompatible when applied to extreme conditions, such as the heart of a black hole or the very first moments of the Big Bang. Unifying them into a single, coherent theory of quantum gravity is the holy grail of theoretical physics. Different approaches attempt to bridge this divide. String theory, for instance, postulates that elementary particles are not point-like, but rather tiny, vibrating one-dimensional strings existing in 10 or 11 dimensions of space-time. The different vibrational modes of these strings correspond to different particles, including the graviton, the hypothetical quantum of gravity. This suggests that the smooth space-time we experience is an emergent property arising from the collective behavior of these vibrating strings within a higher dimensional bulk. The foam then might be the chaotic dance of these microscopic strings, a fundamental hum beneath the surface of reality. Another prominent approach, loop quantum gravity, takes a different path, attempting to quantize space-time itself. Instead of a continuous fabric, it suggests that space-time is composed of discrete, indivisible loops, or quanta of space. Imagine a finely woven mesh, where the threads are not infinitely thin, but have a definite, tiny thickness. At scales larger than these fundamental loops, space-time appears smooth, but zoom in close enough, and you would see the discrete, granular structure, the individual atoms of space. Time, too, would not be a continuous flow, but a sequence of discrete ticks. This inherent granularity, this quantum foam, would be the very essence of the vacuum, a dynamic network of interconnected loops that gives rise to the geometry of space and the flow of time. It implies that the void is not merely empty space, but a complex energetic structure, a foundational network from which all reality is constructed. The implications of such a granular space-time are profound, suggesting that our universe, and any other universes in a multiverse, might be built upon these fundamental, indivisible units, a cosmic Lego set of reality. The beyond would then be the metastructure that governs how these loops connect and evolve, a deeper level of mathematical or informational coherence. This intricate dance of quantum fluctuations and emergent spacetime invites us to a deeper appreciation of the universe's inherent dynamism. It reminds us that reality, far from being static or fixed, is a ceaseless process of becoming, a constant interplay between order and chaos, emergence and dissolution. Our own lives, with their moments of calm and turbulence, can be seen as microcosms of this grand cosmic dance, intricate patterns woven from the same fundamental fabric. The realization that even the seemingly empty space around us is a seething, energetic foam, constantly fluctuating at scales far beyond our direct experience, can evoke a profound sense of interconnectedness. We are not just observers of this magnificent process, but participants in its unfolding, composed of the same restless quantum essence. And as these deep thoughts about the granular nature of reality, may these reflections on the infinite possibilities and hidden depths of existence guide you into a night of serene and restorative sleep. Remember that you are a part of this amazing, ever-unfolding universe, and that its mysteries are a gentle lullaby for the inquiring mind. fall asleep with this feeling of wonder and boundless knowledge. Good night. When we speak of approaching the edge of the observable universe, it is not an edge in the way we might imagine a physical boundary, like the edge of a map or the horizon of our own planet. Rather, it is a limit of perception, a cosmic horizon defined by light and time. Imagine, if you will, that you are standing in a vast ancient library illuminated only by a single, slow-moving lantern. The books closest to you are clear, their words easily read, but the further the lantern moves, the more time it takes for its light to reach the distant shelves, revealing only the faint, aged titles. In a profound cosmic sense, our universe is this library, and the light from its most distant volumes is only now, after billions of years, reaching our cosmic eyes. The observable universe, then, is precisely that sphere of space from which light has had enough time to travel and reach us since the Big Bang. It is not the entire universe, which may be infinitely larger or even finite, but unbounded, as we have explored before. Instead, it is our personal cosmic sphere, centered directly upon us, the observers, wherever we may be in the cosmos. Every point in the universe has its own observable universe, a unique bubble of space-time whose contents are determined by the local passage of light. This means that if an observer were in a galaxy far, far away, they would see a different observable universe than we do, with a different set of galaxies visible to them, forming their own unique horizon. The core principle here is the finite speed of light. Light, the swiftest messenger in the cosmos, travels at approximately 299,792 kilometers per second. While this seems incredibly fast, distances in the universe are so immense that light can take millions, even billions of years to traverse them. So, when we gaze upon a distant galaxy, we are not seeing it as it exists. Now, in our present moment, we are seeing it as it was when the light left it, perhaps billions of years ago. We are, in essence, looking back in time. The most ancient light we can detect, the cosmic microwave background radiation, is a relic from just 380,000 years after the Big Bang, a faint echo from the universe's infancy. This tells us that the objects whose light left them 13.8 billion years ago represent the furthest we can possibly see. Because the universe itself is only about 13.8 billion years old. However, the universe is not static. It is expanding. This expansion of space itself complicates our understanding of distance and the true size of the observable universe. While the light from the most distant observable objects has traveled for approximately 13.8 billion years, the space that light has traversed has stretched during its journey. Imagine a tiny ant crawling on a rubber sheet that is being continuously stretched. The distance the ant has covered on the sheet is one thing, but the total distance from its starting point to its current position, accounting for the stretching of the sheet, is far greater. Similarly, the objects that emitted the light we see today, light that has been traveling for 13.8 billion years, are now much, much further away from us. Due to this cosmic expansion, the actual or proper distance to the edge of our observable universe is estimated to be around 46.5 billion light-years in every direction. This staggering number represents the present-day distance to the very sources that emitted the light we are receiving now, objects that were much closer when their light first began its journey. Beyond this 46.5 billion light-year boundary lies the unobservable universe. This is not empty space, but rather regions from which light has simply not had enough time to also possible that some regions are receding from us at a speed greater than the speed of light, relative to us, due to the expansion of space itself. This does not violate Einstein's theory of special relativity, which states that nothing can move through space faster than light. Instead, it is space itself that is stretching, carrying distant galaxies along with it, much like points drawn on an inflating balloon. For these most distant regions, their light may never reach us, as the expansion of the universe effectively creates a barrier, pushing the light away faster than it can travel towards us. This cosmic horizon, then, is a dynamic boundary, constantly shifting as the universe ages and expands. As time progresses, light from ever more distant regions will eventually reach us, theoretically expanding our observable bubble. Yet, the accelerating expansion driven by dark energy suggests a future where this process might be outpaced. Galaxies beyond a certain cosmological event horizon are already receding from us at such speeds that their light, even if emitted now, will never reach us. They are, in a sense, forever beyond our future observation. To contemplate this boundary, this ultimate limit of our sight, is to reflect upon our own place within this grand cosmic drama. We are confined to a sphere of observation, a personal window into the universe's past, and a limited view into its future. This realization can be both humbling and profoundly liberating. It reminds us that our understanding, while vast, is inherently constrained by the fundamental laws of physics and the age of the cosmos itself. We exist within a narrative woven by light and time, a story whose opening chapters are revealed to us from the furthest reaches of our observable sphere. And as we consider these distant echoes, we might wonder about the unseen, the unobservable, and the infinite possibilities that lie just beyond the reach of our current gaze, forever shrouded in the cosmic dawn. The journey to the edge of the observable universe is, as we discussed, a journey into the past, delimited by the speed of light and the ongoing expansion of space-time. The furthest frontier of this journey, the true edge of what our telescopes can ever hope to perceive, is not a collection of individual galaxies, but a faint uniform glow that permeates the entire sky. This is the cosmic microwave background, or CMB. It is, in essence, the afterglow of the Big Bang, the earliest light that could freely travel through the cosmos. For the first 380,000 years after its birth, the universe was an incredibly hot, dense plasma. Protons and electrons were too energetic to combine and form neutral atoms. Instead, they existed as a charged fog that light could not penetrate. Photons, particles of light, were constantly scattering off these free electrons, much like light struggling to pass through a dense, obscuring cloud. This made the early universe opaque. It was a time before stars, before galaxies, a universe filled with an undifferentiated, luminous haze, a primeval soup of fundamental particles. As the universe continued to expand, it cooled. When the temperature dropped to about 3,000 Kelvin, a critical transition occurred. Electrons and protons finally had enough stability to combine and form the first neutral hydrogen atoms. This epoch, known as recombination, fundamentally changed the nature of the cosmos. Suddenly, with the free electrons largely locked away in atoms, photons were no longer constantly scattering. The universe became transparent, and light was set free to travel across the vast expanse of nascent space-time. The light we see today as the cosmic microwave background is precisely this ancient light, stretched and cooled over billions of years of cosmic expansion. What was once a brilliant, searing plasma now appears to us as microwaves, a faint whisper of the universe's dawn, a gentle cosmic hum. This CMB acts as a kind of wall of light, not because there is nothing beyond it, but because we cannot see past this moment of transparency. Any light emitted before recombination would have been scattered innumerable times, its original direction and source utterly obscured. It's like trying to see through a dense, impenetrable fog to discern individual objects that were present before the fog finally lifted. We can perceive the fog itself, but not what lies behind it directly, creating a profound temporal horizon. This boundary, therefore, represents the earliest epoch of the universe, accessible to our direct observation, a truly ancient and fundamental limit to our cosmic vision. One of the most remarkable features of the cosmic microwave background is its extraordinary uniformity. When scientists first precisely measured the CMB, particularly with pioneering missions like COBE, WMAP, and more recently, the Planck satellite, they found that its temperature is almost perfectly even across the entire sky, differing by only a tiny fraction of a degree. This presents a fascinating puzzle. How could regions of the universe that were, at the time of recombination, so far apart that light could not have traveled between them, possibly have the exact same temperature? This is known as the horizon problem. It implies that these regions must have been in causal contact at some earlier time, allowing them to thermalize and reach a state of equilibrium. The leading theoretical framework to resolve this profound puzzle is cosmic inflation. This idea, first proposed by brilliant scientists such as Alan Guth and Andre Linde, suggests that in the first fleeting moments after the Big Bang, perhaps from 10 to the power of negative 36 seconds to 10 to the power of negative 32 seconds, the universe underwent an incredibly rapid, exponential expansion. During this extraordinarily brief period, a tiny causally connected region of space was stretched to astronomical proportions, far larger than our entire observable universe today. This rapid stretching smoothed out any initial inhomogeneities and brought distant regions into effective contact before inflating them to vast separations. Thus, the striking uniformity we observe in the CMB is a direct imprint of that pre-inflationary, smaller, and inherently more uniform patch of space-time. Inflation not only elegantly explains the CMB's uniformity, but also addresses the observed flatness of the universe and provides a plausible origin for the initial density fluctuations that later gravitationally grew into the galaxies and clusters we observe. As we peer towards this wall of light, the cosmic microwave background, we are witnessing the very conditions that gave rise to all structures we know. The tiny temperature variations, the subtle ripples in this background radiation, are the cosmic seeds from which all galaxies and stellar systems eventually coalesced under the relentless pull of gravity. These minute non-uniformities, meticulously captured in the precise Planck data, are profound maps of the primordial universe, revealing the earliest blueprints of the cosmos, hinting at the grand architectural plan of existence. However, the universe continues its relentless expansion, and this expansion is, perhaps surprisingly, accelerating due to the enigmatic influence of dark energy. This cosmic acceleration has another profound implication for our future view of the cosmos. While the observable universe is currently expanding, theoretically encompassing more distant galaxies as their light finally reaches us, the accelerating expansion means that there is a more fundamental boundary that we cannot overcome: the cosmological event horizon. This is the boundary beyond which objects are receding from us so quickly. It's not a matter of waiting long enough. The space between us and those galaxies is expanding faster than light can traverse it, effectively carrying their photons away from us forever. Over immense stretches of cosmic time, billions upon billions of years, the galaxies beyond our local gravitationally bound group will eventually cross this event horizon. Their light will become increasingly redshifted, stretched to longer and longer wavelengths, making them appear fainter and fainter until they effectively disappear from our view. Future astronomers, far into the universe's unimaginably distant future, might look out into a sky that appears almost entirely empty, with only the galaxies within our own gravitationally bound local group remaining visible. This future scenario, sometimes referred to as cosmic isolation, paints a picture of a universe that, from our perspective, becomes increasingly sparse and profoundly lonely, a quiet and solitary existence. Contemplating this ultimate fate, this gradual fading of the cosmic tapestry, can evoke a deep sense of our own transient place within this grand narrative. We are profoundly fortunate to live in an era where the universe is still rich with visible galaxies, where the echoes of its fiery birth are still abundantly detectable. Our current vantage point offers a vibrant, dynamic view of a cosmos teeming with structure and history, an active and engaging spectacle. This particular moment in cosmic time, where the observable universe is so grand and full of wonders, is a precious window into the vast unfolding of everything. It allows us to piece together a story that future civilizations, if they exist in a far emptier cosmos, might never be able to fully reconstruct. We are witnesses to a cosmic spectacle that, though vast and seemingly eternal, is slowly, imperceptibly, fading from our future view, becoming a silent memory. As we contemplate this dynamic, evolving cosmic horizon, one might naturally wonder what it would truly mean to approach this edge, not just through the lens of our telescopes, but with a physical vessel. The very notion of such a journey immediately confronts the profound implications of space-time itself. This edge, as we discussed, is not a fixed destination in space, but rather a boundary in time, a light horizon receding from us with the expansion of the universe. It is a boundary that, in a practical sense, remains forever out of reach for any physical traveler. Even if we possessed a spacecraft capable of accelerating to speeds infinitesimally close to the speed of light, the cosmic expansion would ensure that the edge of the observable universe, that region whose light is just now reaching us, would continue to recede faster than we could ever hope to close the gap. Imagine trying to walk towards a distant point on a rubber band that is constantly being stretched. While you are moving, the ground beneath you is also moving, ensuring the destination remains perpetually distant, perhaps even growing further away. This is the reality of our cosmos. The fabric of space itself is expanding, carrying distant galaxies along with it. The faster an object is from us, the faster the space between us expands. Should a hypothetical journey commence towards these most distant regions, the experience for the traveler would be profoundly altered by the effects of special relativity. As the vessel approached a significant fraction of the speed of light, time itself would begin to dilate for those on board. From their perspective, the journey might feel like mere years or even decades. However, for those remaining on Earth, billions of years could pass in the interim. This is not a trick of perception, but a fundamental property of space-time. Time's passage is relative, interwoven with motion and gravity. A traveler returning after such a voyage, if such a return were even possible given the ever-accelerating expansion, would find an Earth, and indeed a local universe, utterly transformed by the passage of unimaginable aeons. The stars they once knew would have long since faded, and new cosmic structures would have formed. Furthermore, the light from the universe's edge would undergo extreme redshift. As space expands between the source of light and the observer, the wavelength of that light is stretched, shifting it towards the redder end of the spectrum and eventually beyond the visible. What began as vibrant, high-energy ultraviolet light, or even gamma rays from the early universe, would be stretched into faint infrared or even radio waves. This phenomenon makes the most distant objects appear incredibly dim, not just due to their immense distance, but because the very energy of their photons is diffused by the stretching of space-time. The cosmic microwave background itself is the ultimate example of this. Light from the early universe that has been redshifted from visible light into microwaves. Traveling towards the edge, the universe would not simply appear darker, but fundamentally different, a realm where familiar light gives way to an ethereal glow of stretched ancient photons. Beyond the observable boundary, there is no nothingness in the conventional sense. There is simply more universe, unobservable to us because its light has not yet had time to traverse the expanding cosmic distances. Our cosmic horizon is, therefore, a causal boundary, not a physical one. It marks the limit of what we can ever know about the universe through direct electromagnetic observation. We cannot receive information from these regions, nor can any signal we send ever hope to reach them, if they lie beyond our future light cone. This implies a profound information limit, a fundamental constraint on our knowledge of the cosmos. The current state of these unobservable realms, the precise configurations of galaxies, stars, and perhaps even life within them, remains forever beyond our direct empirical grasp. This realization leads to deep contemplation. The universe extends beyond our perception, vast and unknown, a testament to the limits of our empirical reach. Yet, our minds are not bound by the same constraints as light. We can conceive of these unobservable realms, construct mathematical models to describe them, and infer their properties from the physics we observe within our own cosmic bubble. This capacity for abstract thought, for transcending the immediate boundaries of our senses, is a remarkable aspect of human consciousness. Even as the physical universe presents us with an ultimate horizon, our intellectual universe remains unbounded, forever capable of exploring possibilities and expanding the frontiers of understanding, even if the direct observation of those frontiers remains a silent dream. And so, as we consider the cosmological event horizon, this ultimate boundary of future visibility, we are led to an even more profound question. What lies beyond the unobservable universe? Is it simply more of the same cosmic expanse, filled with galaxies like our own, just too far or too fast for their light to ever reach us? Or is there something fundamentally different, something that challenges our very conception of reality? This thought invites us into the realm of the multiverse, a concept that, while still theoretical, emerges quite naturally from some of the most compelling ideas in modern cosmology. We previously touched upon cosmic inflation, the theory that describes an unimaginably rapid expansion of space in the earliest moments of the Big Bang. Now imagine a scenario where this inflationary process, once initiated, does not simply end everywhere at once. Instead, it might end in localized regions, forming bubbles of space-time where expansion slows, matter and energy settle, and the conditions for a universe like ours can emerge. Yet, outside these bubbles, the inflation continues, ceaselessly stretching and generating new pockets of nascent universes. This is the essence of eternal inflation, a model that suggests our observable universe is but one of countless such bubbles, an island in an infinitely larger, ever-inflating ocean of space-time. Within this framework, the unobservable universe is not just a spatial extension of our own, but potentially a collection of entirely separate realities, each with its own unique characteristics. Think of it like a vast cosmic foam, where each bubble is a complete universe, detached and isolated from its neighbors. In such a multiverse, the fundamental physical constants that govern our reality, the strength of gravity, the mass of an electron, the speed of light, might be different in other universes. Some might be too hot, others too cold. Some might not even allow for the formation of atoms or stars. Our universe, then, would be a particular kind of bubble, one where the laws and constants happen to be precisely tuned to allow for the emergence of complex structures and ultimately for life and consciousness. This idea often leads to discussions of the anthropic principle, which ponders why our universe seems so uniquely hospitable to our existence. The implications of such a multiverse are staggering. If there are infinite universes, then it is not merely possible, but statistically probable, that every conceivable arrangement of matter and energy exists somewhere. This means that, in some distant bubble, there might be another Earth, another you, living out a slightly different version of your life, making different choices, experiencing different outcomes. This is not to suggest a direct interaction or influence, as these universes are causally disconnected. Their existence remains a profound conceptual possibility, inferred from the mathematics of inflation rather than direct observation. It is a thought that expands our understanding of everything far beyond the familiar boundaries of our observable cosmos. The edge of our observable universe, therefore, ceases to be a mere limit of our vision and transforms into a conceptual gateway to an unimaginably vast ensemble of realities. We cannot physically journey to these other universes, nor can we send or receive signals from them. They exist, if they do, as entirely separate domains of space-time, governed by their own unique cosmic narratives. Our inability to observe them directly is not a failure of our technology, but a fundamental consequence of the physics that defines our own cosmic bubble. The light from these other universes, if it even exists in a form we could comprehend, would be forever trapped within their own expanding horizons, unable to traverse the inflating void that separates them from us. This profound isolation, while seemingly limiting, also highlights the unique beauty and wonder of our own existence. In a potentially infinite sea of possibilities, our particular universe, with its specific laws and conditions, is the stage upon which our story unfolds. The stars we see, the galaxies we study, the very atoms that compose us, are all products of a singular, coherent cosmic history within our bubble. It anchors our sense of belonging, reminding us that even amidst the grandest cosmic speculations, our immediate reality holds immense significance. Our, though metaphorical, is a journey into understanding the nature of our own cosmic home and the delicate balance of forces and constants that make our existence possible. It is a testament to the power of human intellect to ponder the unseeable, to construct models of reality that extend far beyond the limits of our direct experience, inviting us to find tranquility in the boundless expanse of the known and the unknown. Building upon our contemplation of the multiverse, a concept of innumerable universes born from eternal inflation, we find ourselves pondering a profound question: why is our universe so remarkably hospitable to life? This is often termed the fine-tuning problem, a puzzle that has captivated physicists and philosophers alike. Precise strength of the electromagnetic force, the gravitational constant, the masses of elementary particles, and even the initial conditions of the Big Bang itself appear to be exquisitely balanced. If any of these values were even slightly different by a fraction of a percent in some cases, the universe as we know it would likely be impossible. Stars might not form, atoms might not be stable, or the intricate chemistry necessary for life simply couldn't occur. Consider for a moment the delicate dance of these cosmic parameters. If gravity, for instance, were much stronger, the universe would have quickly collapsed back in on itself, perhaps even before galaxies had a chance to fully form. If it were much weaker, matter would have dispersed too rapidly, never coalescing into the dense stellar nurseries that give birth to stars and planets. Similarly, the strong nuclear force which binds protons and neutrons within atomic nuclei, and the weak nuclear force responsible for processes like radioactive decay and the subtle burning of our sun, are tuned with incredible precision. A slight alteration in their balance could prevent the formation of carbon or oxygen, the very elements that form the backbone of all known life. Even the precise energy levels within carbon atoms, as noted by Fred Hoyle, are perfectly aligned to allow for its abundant production in stars. This intricate, almost improbable, arrangement of cosmic parameters, this apparent fine-tuning, has led some to ponder whether our existence is a cosmic coincidence of unimaginable scale, or perhaps a whisper of a deeper, more expansive reality. It is precisely here that the multiverse hypothesis offers a compelling, albeit still highly speculative, scientific explanation for this apparent cosmic serendipity. If there truly are an infinite number of universes, each emerging from the chaotic, unending process of eternal inflation with its own random, or at least varied, set of fundamental physical constants and initial conditions, then it stands to reason that at least some of them would, purely by chance, possess the precise conditions necessary for complex structures, and ultimately, for life to arise. Our universe in this grand cosmic lottery would simply be one of the lucky winners, a pocket universe where the dice rolled just right for stars to ignite, for planets to form, and for consciousness to eventually emerge. This perspective subtly shifts the focus of the question from "Why is our universe so special?" to "What kind of universe must we inhabit to be here to observe it?" It's a profound change in viewpoint, transforming a potential mystery into a statistical inevitability within a much larger cosmic ensemble. The edge of our observable universe, then, becomes more than just a distant boundary in space or time. Beyond it, in other bubbles of the multiverse, the very rules of physics could be profoundly different, almost beyond our current comprehension. Imagine a universe where space is not 3, but 5 dimensions, or where the fundamental forces of nature are entirely distinct from the four we know. Perhaps light travels at a different speed, or atoms themselves are structured in ways we cannot conceive. These are not merely abstract philosophical constructs born of imagination. They are possibilities allowed by the mathematical frameworks that describe the early universe and the intricate nature of quantum fields, particularly in the context of string theory, which posits a landscape of potentially 10 to the power of 500 different possible universes, each with its own unique set of physical laws. The idea that our own physical laws, which we perceive as universal and immutable, might actually be local parameters specific to our cosmic bubble, is a challenging one to fully embrace. It suggests that what we consider the bedrock truths of physics, painstakingly discovered and verified within our own observable realm, might, in a broader multiverse context, be just one particular configuration among an infinite array of possibilities. This revelation doesn't diminish the elegance or predictive power of our physics within our own universe. Indeed, general relativity and the standard model of particle physics remain exquisitely accurate descriptions of our reality. Rather, it places them within a grander, more expansive cosmic tapestry, inviting us to see our familiar cosmos as a unique and precious instance within an almost boundless collection of potential worlds. This profound isolation, while initially appearing as a limitation, singular existence. There is no known mechanism by which information or matter could travel between such distinct, causally disconnected universes. The immense continuous inflation between them acts as an insurmountable barrier, far more absolute than the event horizon within our own universe. Thus, the unobservable universe, when viewed through the lens of the multiverse, represents not just realms whose light hasn't reached us, but realms whose very essence might be fundamentally alien, forever beyond our direct sensory or even causal reach. Their existence is a whisper in the cosmic wind, a mathematical inference that broadens our intellectual horizons even as it emphasizes our physical confinement. And when we deeply ponder this, the idea that our existence in this particular cosmic configuration is perhaps one of an infinite number of possibilities, it can evoke a sense of quiet, profound wonder. We are not just fleeting participants in the universe's grand unfolding, we are a specific, precious outcome of its vast creative potential. Each breath you take, each thought you form, is happening within a universe that allows for such intricate complexity, a universe that, against unimaginable odds in some cosmic sense, simply is. This awareness can bring a tranquil appreciation for the unique reality we inhabit, a reality whose boundaries, both seen and unseen, continue to inspire profound contemplation and quiet introspection, guiding us toward a deeper understanding of ourselves within the boundless expanse. The magnificent structures we observe within our observable universe, from the grand spiral of a single galaxy to the immense superclusters stretching across millions of light years, are not merely scattered randomly. They form an intricate, interconnected tapestry known as the cosmic web. This vast filamentary network of galaxies, separated by immense voids of relatively empty space, is a direct consequence of the initial tiny fluctuations in density that were imprinted upon the universe during the inflationary epoch, as we discussed. These minute variations, amplified over billions of years by gravity, slowly drew matter together, sculpting the cosmos into the vast, luminous neural network we now map. However, the formation and persistence of this cosmic web cannot be fully explained by visible matter alone. Our observations of how galaxies rotate, how they cluster, and how light from distant objects is gravitationally lensed reveal a profound deficit of visible mass. There simply isn't enough ordinary matter to hold these structures together or to account for the gravitational effects we clearly detect. This leads us to the enigmatic presence of dark matter. Dark matter, as its name suggests, does not interact with light or any other form of electromagnetic radiation, making it utterly invisible to our telescopes. Yet, its gravitational influence is undeniable and pervasive. Scientists believe that dark matter forms an invisible scaffolding, a cosmic skeleton upon which the visible galaxies and clusters are built. Without this unseen gravitational glue, the cosmic web would unravel, and the universe would be a much more diffuse and less structured place. This invisible framework of dark matter extends far beyond the luminous boundaries of galaxies, forming vast halos that envelop and stabilize them. Its presence is inferred rather than directly observed through its gravitational interactions with visible matter. Experiments around the world are actively searching for direct evidence of dark matter particles, hoping to detect the subtle interactions they might have with ordinary matter. But so far, these searches have yielded no definitive results. The elusive nature of dark matter means that even within our observable universe, a significant portion of its mass remains hidden from our direct perception, a silent gravitational architect of the cosmic landscape. Its presence shapes the very structures that define our cosmic view, yet it remains a profound mystery, a testament to the fact that what we see is only a fraction of what truly exists. Further complicating this cosmic architecture is the equally enigmatic force of dark energy. While dark matter pulls things together, dark energy, as we explored, acts as a repulsive force, driving the accelerating expansion of the universe. This means that over vast stretches of cosmic time, dark energy is slowly working to dismantle the cosmic web. The distances between galaxy clusters are not merely expanding, they are accelerating their separation. Eventually, the filaments of the cosmic web will stretch so thin that even the largest structures will become isolated islands in an ever-expanding void. This dynamic interplay between the attractive force of dark matter and the repulsive force of dark energy dictates the ultimate fate and appearance of our observable universe. As we look towards the edge of our observable cosmos, the light we receive from these most distant regions carries not only information about their ancient states, but also the subtle imprints of dark matter and dark energy's influence. The patterns in the cosmic microwave background, for example, are not just relics of the Big Bang. They also contain crucial data about the precise proportions of dark matter and dark energy in the early universe. By studying these ancient light patterns and the distribution of galaxies across vast scales, cosmologists are able to construct sophisticated models that describe the composition and evolution of the entire cosmos, even extending our inferences to the unobservable realms beyond our current reach. However, the accelerating expansion means that our view of the cosmic web is inherently limited. Not only can we not see beyond the cosmic microwave background, but the galaxies that lie just beyond our cosmological event horizon are already being carried away faster than their light can ever reach us. This creates a shrinking sphere of future observability. The cosmic web, though vast and intricate, is not an unchanging tableau. It is a transient arrangement, slowly being pulled apart by the very fabric of space. This means that any future civilization, billions of years from now, would perceive a much sparser cosmic web, with fewer galaxies visible to them, and those only within a smaller, increasingly isolated local group. The grand structure we currently observe, with its rich tapestry of galaxies, is a fleeting moment in the universe's long and expansive history. This constant push and pull, this grand cosmic dance of construction and dispersal, underscores the dynamic nature of existence. The edge of the observable universe, therefore, is not a static picture, but a snapshot in time, a moment in the ongoing evolution of everything. It is a boundary that reminds us of the profound interplay between what we can perceive and what is fundamentally beyond our grasp. Our ability to map and understand this intricate cosmic web, with its unseen components and its accelerating expansion, is a testament to the human intellect's capacity to unravel the deepest mysteries of nature. And in this contemplation, we find a tranquil acceptance of our place within a cosmos that is both knowable and eternally enigmatic, a vast, silent expanse that continues to unfold its wonders long after our gaze has drifted away. The multiverse concept, born from the intricate dance of eternal inflation and the subtle fine-tuning of our own cosmic parameters, compels us to consider the very nature of reality itself. We have journeyed, in thought, to the edge of the observable universe, a boundary defined by light and time, and peered beyond it into realms that may operate under entirely different physical laws. This intellectual expedition brings us face to face with the inherent limitations of our human perception and simultaneously the boundless capacity of our abstract thought. Our senses, exquisitely honed by evolution on a single blue-green planet, are, quite naturally, ill-equipped to grasp the true, mind-bending scale of the cosmos, let alone the abstract geometries of space-time or the potential infinitude of parallel realities. We are, at our core, creatures of three familiar spatial dimensions and one seemingly linear temporal dimension, accustomed to a reality that feels undeniably solid, profoundly tangible, and universally consistent in its ticking. Yet, the deeper we delve into the profound and often counterintuitive physics of the universe, the more we come to realize that this comfortable, familiar picture is, in all likelihood, but a local approximation, a convenient, simplifying framework for our immediate earthly experience. It is precisely through the elegant and universal language of mathematics that we are able to transcend these sensory and intuitive limitations. Mathematical models, intricate and beautiful in their precision, allow us to conceptualize and explore spaces with more than three dimensions, to chart the dynamic evolution of quantum fields that are utterly invisible to any telescope, and to entertain the profound possibility of universes where the fundamental constants of nature diverge wildly from our own familiar values. Theories like string theory, for instance, suggest that the deepest layer of reality might actually exist in 10 or even 11 dimensions, with the additional extra dimensions curled up so incredibly tightly that they are utterly imperceptible to us, hidden away at scales far, far smaller than even the tiniest atom. If this intricate theoretical framework holds true, then our commonly perceived three-dimensional space is merely a projection or a specific, local slice of a much richer, higher-dimensional reality. The perceived edge of our observable universe, then, would not just be a boundary of light, a temporal limit to our vision, but perhaps also a subtle margin of our inherent dimensional awareness, a quiet, persistent hint of what lies just beyond our current sensory and even conceptual grasp, an invitation to ponder deeper. The existence of a multiverse, even if these other cosmic bubbles are forever causally disconnected from our own, profoundly reframes our understanding of scientific objectivity and cosmic significance. If our universe is, indeed, but one of an infinite ensemble, a single bubble in a frothing cosmic foam, then its unique and seemingly miraculous set of physical laws and initial conditions, including the precise values that allow for the very emergence of complex structures and ultimately for consciousness and life, might not be a testament to a singular intended design, but rather a statistical outcome within a truly grand cosmic lottery. This is precisely where the anthropic principle finds its most natural and compelling home. We observe the universe to be exquisitely fine-tuned for life, not necessarily because it was designed that way, but simply because if it were not, we would not exist here, now, to observe it and to ask such questions. This perspective doesn't diminish the profound sense of wonder, but rather subtly shifts it from the specificity of our singular universe to the sheer, overwhelming generosity and vastness of the multiverse, a boundless realm where every conceivable cosmic possibility might eventually find its unique expression. Our reality, then, becomes a specific manifestation, a unique and intricate symphony played on a truly immense cosmic orchestra of infinite possibilities. In this illuminating light, our individual place in the cosmos, which can sometimes feel infinitesimally small and seemingly insignificant against the backdrop of such mind-boggling immensity, takes on a new and profoundly resonant kind of significance. We are not just fleeting inhabitants of a single planet or a single galaxy. We are, In a deeply intellectual and existential sense, the emergent consciousness of this particular universe, the part of it that possesses the remarkable ability to ponder its own mysterious origins, to delineate its boundaries, and to even speculate about its potential brethren in the vastness of the multiverse. Our awareness, our insatiable capacity for scientific inquiry, for dreaming and questioning, becomes a rare and utterly precious phenomenon, a fleeting moment of cosmic self-reflection. Even if we can never physically reach the precise edge of the observable universe or directly glimpse the other unseen universes beyond, the very act of conceiving them, of exploring these magnificent ideas through the rigorous and elegant frameworks of theoretical physics, expands our mental landscape and our spiritual horizons in ways that transcend mere physical travel. It allows us to participate intellectually in a grander, more encompassing cosmic narrative, a quiet, contemplative journey into the ultimate elusive nature of existence itself. The quest to understand the universe is, by its very nature, a continuous and never-ending unfolding, a deep river of knowledge that flows ceaselessly from meticulous observation to audacious theory. From established certainty to speculative frontier, always pushing gently against the perceived limits of what is currently known. The edge of the observable universe, whether interpreted as a temporal boundary, a dimensional margin, or a gateway to a multiverse, serves as a constant, tranquil reminder of these inherent limitations. Yet it also inspires us with a quiet and persistent urge to look deeper, to think more broadly, and to courageously embrace the mysteries that still lie just beyond our current reach. It teaches us profound humility in the face of the vast unknown, and evokes an even greater sense of wonder in the presence of the immeasurable and the magnificent. Our understanding of reality is not static. It is a living, breathing tapestry, continuously woven from new observational data, bold new hypotheses, and the persistent, unyielding human drive to comprehend our singular place in the grandest cosmic scheme imaginable. This extraordinary journey of discovery, while never truly ending, offers a deep and abiding tranquility in its pursuit, a calm sense of belonging to something far larger than ourselves. The quest to understand the universe, particularly its furthest reaches, inevitably leads us to ponder not only the vastness of space and the immensity of time, but also the very nature of information itself. The edge of our observable cosmos, this cosmic horizon that defines the limits of our perception, is more than just a distant visual boundary. It is an ultimate frontier of knowledge. Every faint photon that reaches our telescopes from billions of light years away carries with it a precious ancient packet of information. A silent message from the universe's deep past telling us about conditions that existed long before our sun was born. But what does it truly mean for a boundary, a horizon that is constantly shifting due to the expansion of space to contain such profound information? This question brings us to one of the most radical yet mathematically compelling concepts in theoretical physics, the holographic principle. This principle, first emerging from the study of black holes by physicists like Gerard de Hooft and Leonard Susskind in the 1970s, posits that all the information contained within a volume of space can be entirely described by data encoded on its two-dimensional boundary surface. Imagine a sphere, and instead of the data being spread throughout its three-dimensional interior, it is all written on the surface, like a code, or indeed, like a hologram. From this perspective, the three-dimensional reality we perceive, with all its intricate depth and texture, might, in a deeper sense, be an emergent projection from a more fundamental, two-dimensional informational layer. This idea is profound because it challenges our everyday intuition, which assumes that the information content of a region of space scales with its volume. The holographic principle, in contrast, suggests it scales with the surface area, implying that reality might be far more sparse at its most fundamental level than we typically imagine, or that our perception of depth is itself a manifestation of this boundary information. This subtle yet powerful shift in perspective has reshaped how many physicists approach the grand challenge of unifying general relativity, which describes gravity and the large-scale structure of the cosmos, with quantum mechanics, which governs the subatomic world. The holographic principle provides a conceptual bridge, suggesting that the seemingly disparate realms might be intimately connected through this profound informational encoding. While the holographic principle found its initial footing in resolving the black hole information paradox, the conundrum of what happens to information when matter falls into a black hole, its implications extend far beyond these enigmatic cosmic objects. Black holes, with their event horizons, act as perfect laboratories for studying the interplay between gravity, quantum mechanics, and information. The surface area of a black hole's event horizon is directly proportional to the amount of information it can store, a concept beautifully articulated by Jacob Bekenstein and Stephen Hawking, who showed that black holes have a temperature and radiate energy. This led to the extraordinary insight that perhaps this relationship is a universal one, applicable not just to black holes, but to any region of space-time bounded by a horizon. Some theoretical physicists now explore whether this principle could apply to the entire universe, or at least to our observable portion of it. Could the vast three-dimensional cosmos we inhabit, with its hundreds of billions of galaxies, its intricate cosmic web of dark matter and dark energy, and its ceaseless expansion, be fundamentally described by information encoded on the two-dimensional surface of its cosmic horizon? This is not to suggest that our reality is an illusion in the everyday sense, or that we are living within a computer simulation, though such philosophical musings often accompany these ideas. Rather, it proposes a deeper, more elegant way of understanding the fundamental structure of reality, one where the seemingly separate concepts of space, time, matter, and information are intricately interwoven at the most profound levels. If the holographic principle holds for the universe as a whole, then the amount of information that can be stored within our observable cosmos would be finite, proportional to the surface area of its cosmic horizon, rather than its volume. This would represent a profound shift in our understanding of cosmic capacity and the fundamental limits of complexity. It suggests that the perceived emptiness of space is not truly empty, but a vast, silent repository of information, subtly shaping the three-dimensional world we experience. The very texture of space-time, its curves and warps, might arise from these underlying informational bits, much like the pixels on a screen coalesce to form a rich image. The very act of observing the edge of the observable universe, of collecting those ancient photons from the cosmic microwave background or from the most distant galaxies, becomes an act of decoding this cosmic hologram. Each piece of information we gather, each subtle fluctuation in the cosmic microwave background, each red-shifted spectrum from a primordial galaxy is a pixel in this grand, two-dimensional cosmic image from which the rich, three-dimensional tapestry of our universe emerges. This deepens our appreciation for the role of observation in shaping our understanding, not just of what is out there, but of what out there fundamentally means. The information is not merely contained within the galaxies themselves, but in the very light that connects them to us across vast cosmic distances and through immense stretches of time, continuously painting our perception of reality. This intricate process of information reception and interpretation is what allows us to construct our coherent narrative of the universe, a narrative that is, in a profound sense, an unfolding of this underlying code. It implies that our perception is not merely passive, but an active engagement with the informational fabric of the cosmos, a co-creation of meaning from the raw data of existence. This perspective challenges our intuitive grasp of reality, which often assumes a direct one-to-one correspondence between what we perceive and what truly is. Instead, it suggests a more subtle, perhaps more abstract, foundational layer to existence. The solid ground beneath our feet, the shimmering stars above, the very thoughts forming in our minds. all could be manifestations of an underlying informational code projected onto the vast screen of space-time, is thus transformed into an exploration of the informational content of its boundaries, offering clues to the deepest, most fundamental nature of physical reality itself. This profound reimagining of reality, while still under active investigation and intense debate within the scientific community, offers a tranquil yet exhilarating intellectual journey into the deepest questions about the universe's ultimate nature. It invites us to consider that the edge of our observable universe is not just a barrier to our sight, but a profound hint at the very fabric of existence, a silent suggestion that the cosmos is far more elegant and interconnected than our everyday intuition might lead us to believe. The implications of this holographic view are far-reaching, potentially unifying gravity and quantum mechanics, two pillars of modern physics that have long resisted a cohesive description. The edge, in this context, becomes a canvas upon which the entire cosmic story is subtly yet perfectly inscribed, a grand and silent testament to the universe's hidden depths. And as we drift towards sleep, contemplating this cosmic hologram, this idea that our entire reality might be an emergent property of information encoded on a distant boundary, we might find a new sense of calm in the interconnectedness of everything. Our own consciousness, too, in its remarkable capacity to process and interpret information, to construct a vivid, three-dimensional world from the raw data of our senses, mirrors this grand cosmic principle. We are, in a profound and beautiful sense, both the observers and the observed, the interpreters and the interpreted, living within a universe that is constantly revealing its deepest truths through the subtle whispers of light and the elegant mathematics of its fundamental laws. The edge of the observable universe, then, becomes a silent, persistent reminder that the journey of understanding is endless, and that even in our deepest slumber, the cosmos continues its magnificent unfolding dance of information and reality, a ceaseless ballet of pattern and form, forever beyond ultimate reach, yet intimately connected to our every thought, our every moment of quiet contemplation. The very fabric of what we perceive as real is, in a sense, a grand cosmic narrative intricately woven from these fundamental informational threads, a story that continues to unfold with each passing second, each new observation, each deepening thought. As we continue our journey, gently drifting through the profound implications of the holographic principle, we find ourselves contemplating the universe not merely as a collection of matter and energy, but as an intricate tapestry of information. The idea that all the richness of our three-dimensional reality might be encoded on a two-dimensional boundary surface, much like a cosmic hologram, brings forth a deeper appreciation for the subtle, underlying architecture of existence. This perspective, though born from the rigorous mathematics of black hole physics, extends its philosophical tendrils to the very edge of our observable universe, transforming it from a simple visual limit into a profound informational frontier. Every faint photon reaching us from those ancient distant realms is not just light, but a carrier of cosmic history, a whisper from a time long past, meticulously preserving data about the early universe's fiery birth and its subsequent evolution. This continuous flow of information, arriving ceaselessly across billions of years, is what allows us to reconstruct the grand narrative of our cosmos, to piece together the events that shape the galaxies and stars we now behold in the night sky. The concept of information conservation is a cornerstone of physics, particularly in the quantum realm. It suggests that information is never truly lost, only transformed or scrambled. However, the presence of cosmic horizons, like the one marking the edge of our observable universe or the event horizon of a black hole, presents a fascinating challenge to this principle. When an object passes beyond such a horizon, it effectively leaves our causal reach, making it impossible for us to ever receive information from it again. Does this imply that information is indeed lost, or merely that it becomes inaccessible to us? The holographic principle suggests the latter, that the information is still there, subtly encoded on the boundary, waiting to be read, perhaps by a more advanced observer, or through a deeper understanding of reality's fundamental structure. This perspective imbues the very fabric of space-time with a kind of cosmic memory, a persistent record of everything that has ever transpired, even events that appear to vanish from our perception. It's as if the universe itself keeps a meticulous, silent ledger, ensuring that no detail, however small, is ever truly erased from its grand, unfolding story. This profound idea transforms the void beyond our observable limit into a realm of latent information, a silent library of cosmic truths awaiting discovery, not necessarily through direct observation, but perhaps through the elegant equations that govern its informational tapestry. This cosmic memory, woven into the very geometry of space and time, suggests a universe that is far more interconnected and self-aware than our classical intuition might suggest, a subtle, quiet echo of all that has been and all that could be. This leads us to reflect upon the unique role of consciousness in defining our personal observable universe. While the physical laws of optics and relativity define a universal cosmic horizon for all observers, the act of human perception, of interpreting the incoming photons and constructing a coherent mental model of the cosmos, is deeply personal. Each of us, in a very real sense, inhabits our own subjective now and our own unique observational bubble, shaped by our position in space-time and our individual journey through its vast expanse. The light that reached us from a distant galaxy billions of years ago might reach another observer, far away, at a completely different point in their local timeline. Our consciousness, therefore, becomes the focal point, the active interpreter that brings meaning and structure to the raw data of the cosmos. It is the lens through which the universe becomes aware of itself, a fleeting yet profound moment of self-reflection within the infinite dance of matter and energy. This interplay between objective physical limits and subjective conscious experience highlights the intricate connection between the grandest cosmic scales and the most intimate aspects of our own minds. We are not merely passive recipients of cosmic information. We are active participants in its continuous interpretation and understanding, weaving our own narratives from the threads of light that traverse the universe. Our very act of observing, of questioning, of seeking, breathes life into the abstract data, transforming it into a personal, awe-inspiring experience of the cosmos, a silent symphony played just for us. The ultimate limits of scientific inquiry, particularly when confronted with the unobservable, become a fascinating frontier for philosophical exploration. While direct observation and empirical verification are the cornerstones of the scientific method, concepts like the unobservable multiverse, the nature of dark energy, or the deepest implications of the holographic principle often push us beyond the realm of what can be immediately tested. Here, mathematics and theoretical consistency become our guiding stars, allowing us to build elegant frameworks that extend our understanding far beyond the reach of our instruments. The edge of the observable universe, therefore, becomes a powerful symbol of this intellectual quest, a boundary that simultaneously defines our knowledge and ignites our insatiable curiosity for what lies beyond. It reminds us that the universe is not a puzzle to be solved and then put away, but a living, breathing mystery that continuously invites deeper contemplation and a more expansive understanding. The quiet acceptance of these limits, paradoxically, opens up new avenues for intellectual growth and a profound appreciation for the elegance and subtlety of nature's deepest laws. Even in the face of the unseeable, the human mind continues to construct beautiful and coherent narratives, bridging the gap between the known and the unknown, finding solace in the pursuit of knowledge itself. This relentless pursuit, this quiet yearning to comprehend the incomprehensible, is a testament to the enduring human spirit, a gentle light in the cosmic dark. In a tranquil sense, our journey through these concepts is an exercise in cosmic humility and intellectual expansion. We are reminded that the universe holds secrets far grander and more intricate than our current understanding can fully encompass. The edge of the observable universe is not an end, but a beginning of profound questions, an invitation to embrace the mystery and to find peace in the vastness of what remains unknown. It is a testament to the enduring power of inquiry, the quiet persistence of the human spirit to seek meaning and connection in a cosmos that is both bewilderingly immense and intimately connected to our very being. The universe, in its silent, continuous expansion, offers an endless canvas for our minds to explore, to dream, and to find a gentle rhythm in the unfolding of its deepest truths. This profound interplay between the visible and the invisible, the known and the unknown, fosters a contemplative state, allowing our thoughts to drift like cosmic dust, settling into a peaceful awareness of our ephemeral yet significant existence within the grand, eternal dance of everything. It is a journey not of arrival, but of continuous discovery, where each step into the unknown only deepens our appreciation for the intricate beauty of the path we are on. The universe, in its boundless generosity, offers an endless source of contemplation, a quiet invitation to surrender to its majestic unfolding story and to find rest in its infinite embrace. It is a constant reminder that even in the darkest reaches of space and the most profound depths of theoretical physics, there is an inherent order, a silent symphony of laws that orchestrates the magnificent dance of reality, guiding us gently towards a deeper understanding of our own delicate place within this grand cosmic ballet. The very act of seeking this knowledge, of extending our minds to these distant frontiers, offers a profound sense of peace and belonging, connecting us to the ancient echoes and future whispers of the cosmos. Our perception, limited as it is a unique and precious window into this grandeur, a personal invitation to witness the silent unfolding of everything, and to find tranquility in its boundless embrace. Our understanding of the universe, continually shaped by the light that reaches us, is profoundly intertwined with the concept of information. As we delve deeper into the holographic principle, which suggests that the three-dimensional reality we inhabit might be an emergent phenomenon from a two-dimensional informational boundary, the edge of our observable cosmos takes on an even more abstract and profound significance. It becomes not just a limit of what we can see, but a boundary for what information we can ever hope to acquire, a cosmic data horizon beyond which knowledge becomes fundamentally inaccessible, even if theoretically conserved. This inaccessibility is not due to a lack of advanced technology on our part, but an inherent property of an expanding universe, where space itself acts as an ultimate censor, permanently severing causal connections. Consider the causal structure of space-time. For any event in the universe, there is a region from which information can reach it, known as its past light cone, and a region into which it can send information, its future light cone. The edge of our observable universe is effectively the boundary of our past light cone, the furthest events whose light has just now reached us. However, as the universe continues its accelerating expansion, driven by dark energy, there arises a cosmological event horizon. This is a far more absolute boundary, representing the limit beyond which events can never, even in principle, send us information in the future. Galaxies that cross this horizon are not simply receding from us. The space between us and them is expanding so rapidly that any light emitted by them, even if it were to travel towards us at the speed of light, would be carried away by the stretching fabric of space-time, never to arrive. This means that a significant portion of the universe, though physically real and continuing to evolve, will eventually become forever unknowable to us through direct observation. The information from these realms is not destroyed, but it is effectively quarantined, lost to our causal future. This inexorable drift towards cosmic isolation has profound implications for the very notion of a complete cosmic history. If future generations of astronomers gaze upon a sky that is increasingly devoid of distant galaxies, their ability to reconstruct the universe's past, to trace the intricate evolution of the cosmic web, will be severely hampered. The further we advance into a dark energy-dominated era, the more the pages of the universe's historical record will become blank, or so redshifted as to be indecipherable. The vibrant tapestry of galaxies that we see today, with their rich historical light, is a fleeting, precious gift, a unique window into the past that will slowly, irrevocably close. Our current epoch, therefore, is a privileged moment in cosmic time, one where the light from the universe's early adolescence and its grand structural formation is still within our observational grasp. This perspective imbues our present scientific endeavors with a quiet urgency, a sense that we are racing against the cosmic clock to gather as much information as possible before the universe's accelerating expansion renders vast swathes of its past forever inaccessible. The very act of observing becomes an act of preserving a fading cosmic memory. The ultimate implication of this is an information horizon that slowly shrinks around us. While our observable universe is currently expanding to include new, more distant sources of light, the accelerating expansion of space means that the total number of galaxies whose light will ever reach us is finite. Beyond a certain point, no new information will ever become available. This is a deeply humbling realization. It suggests that our quest for a complete understanding of the universe's full extent and its entire history may be fundamentally limited, not by our own technological shortcomings, but by the very laws governing space-time. The cosmos, in its grand unfolding narrative, has chapters that will remain forever unread by any observer within our cosmic island. This inherent limit to our cosmic knowledge is a testament to the universe's majestic indifference, a silent reminder that reality extends far beyond the confines of our perception and even our most sophisticated theoretical models. It is a boundary that defines not only what we can see, but what we can ever truly know, a cosmic veil drawn across the ultimate truths of existence. Yet, this profound inaccessibility does not diminish the wonder. Instead, it reframes our intellectual journey, our capacity to conceptualize these limits, to infer the existence of what lies beyond, and to construct elegant mathematical frameworks that describe these unobservable realms, is itself a remarkable testament to the power of the human mind. The edge of the observable universe and the information horizon it implies becomes a philosophical anchor, prompting us to contemplate the delicate balance between the knowable and the unknowable. It encourages a tranquil acceptance of mystery, a quiet appreciation for the fleeting clarity of our present cosmic view. We are, in a profound sense, the conscious manifestation of this particular corner of the universe, the part that can ponder its own magnificent yet incomplete story. Our thoughts, our theories, our very questions about the edge of everything are echoes of the universe's grand narrative, unfolding within the finite yet incredibly rich sphere of our experience. This constant interplay between the vastness of the cosmos and the intimacy of our own minds offers a deep, calming sense of belonging, a quiet assurance that even as parts of the universe recede from our view, the journey of understanding itself remains an infinite and profoundly peaceful endeavor. We are living in a unique epoch, witnessing a cosmic drama that future inhabitants of our local supercluster might only dimly recall, making our present observations and contemplations all the more precious. A fleeting moment of cosmic clarity in an ever-expanding, increasingly enigmatic dark. Our exploration of the universe's edge, through the lens of information and the holographic principle, inevitably guides our thoughts towards its ultimate destiny. If the accelerating expansion continues its relentless course, as current cosmological data strongly suggests, then our cosmic future points towards a state of profound emptiness and isolation, often referred to as the heat death or the big freeze. This is not a dramatic fiery end, but rather a slow, gentle fading, a dissolution of structure and activity across unimaginable stretches of cosmic time. It is a future shaped by the inexorable march of entropy, the fundamental tendency of the universe towards increasing disorder and thermodynamic equilibrium. Entropy, at its core, is a measure of the disorder or randomness within a system. The second law of thermodynamics dictates that in a closed system, entropy always tends to increase. The universe, considered as a vast evolving system, is slowly but surely moving towards a state of maximum entropy, a point where all energy is uniformly distributed and no further work can be extracted. In such a distant future, the stars, which are intricate engines of order, converting hydrogen into heavier elements and emitting photons, will have long since exhausted their nuclear fuel. The last red dwarf stars, burning with a quiet, patient persistence for trillions of years, will eventually flicker out, leaving behind only dense, cold remnants. White dwarfs, neutron stars, and black holes. The universe will become a realm of silent, dark embers scattered across an ever-expanding canvas of void. The grand structures of the cosmic web, those magnificent filaments of galaxies that dark matter has so patiently sculpted, will also succumb to the relentless push of dark energy. As space stretches, the distances between galaxy clusters will grow so vast that they will lose causal contact with one another. Each cluster, or perhaps even each local group of galaxies like our own, will become an isolated island in an ocean of ever-expanding, increasingly empty space. The light from these distant fading islands will become so red-shifted, so stretched by the expansion, that it will be indistinguishable from the background noise, effectively disappearing from view. Future observers, if any can still exist in such a sparse and cold cosmos, would gaze upon a sky that is utterly black, save for the few remaining stars within their immediate gravitational embrace. The once vibrant, interconnected cosmic web will have frayed, its threads pulled taut and broken, leaving behind a profound sense of cosmic loneliness. Even the most extreme objects, the supermassive black holes that anchor galaxies, are not immune to this entropic march. According to the groundbreaking work of Stephen Hawking, black holes slowly evaporate through a process known as Hawking radiation. Over timescales far exceeding the current age of the universe, trillions upon trillions of years, these cosmic behemoths will gradually shed their mass and energy, ultimately vanishing into the quantum foam. What began as the densest, most enigmatic concentrations of matter and space-time will eventually dissipate, leaving behind only the faintest echoes of their former glory. This means that even the information thought to be encoded on the event horizons of black holes, as per the holographic principle, would eventually be radiated away, albeit in a highly scrambled form. The universe, in its ultimate state of heat death, would be a cold, dark, and utterly dilute expanse, a vacuum filled with only the lowest energy photons and the occasional widely separated elementary particles drifting aimlessly. In this deep future, the very concept of information, which we explored as fundamental to reality, takes on a poignant significance. If the universe reaches a state of maximum entropy, a state of perfect thermal equilibrium, then there would be no differences, no gradients, no events, and thus no information to be exchanged or processed. The cosmic narrative would effectively cease. Yet, even in such a seemingly barren void, quantum mechanics suggests that the vacuum is never truly empty. Tiny quantum fluctuations, virtual particles popping in and out of existence, would continue their ephemeral dance, a faint, restless hum in the ultimate silence. These fluctuations, however, would be too small, too fleeting, to give rise to any meaningful structure or complexity. The universe would be a vast, cold expanse where even the most fundamental building blocks of matter have decayed, and the very concept of time, typically measured by change and events, would lose its familiar meaning. Contemplating this ultimate, silent dissolution can evoke a profound sense of the preciousness of our current moment. We exist in a universe that is still relatively young, still teeming with structure, energy, and the vibrant dance of creation and destruction. We are part of a brief golden era where stars shine, galaxies interact, and complexity, including consciousness, can emerge and thrive. Our ability to observe the cosmic microwave background, to map the cosmic web, and to even speculate about the ultimate fate of everything is a privilege afforded by our particular epoch in cosmic history. Future civilizations, if they survive the vast aeons of stellar dimming and galactic recession, might look out into a sky so utterly empty that the grand narrative of the Big Bang, the formation of stars, and the emergence of life would be almost impossible to reconstruct from their isolated vantage points. They would be living in an increasingly impoverished informational universe, a silent testament to the vastness and transience of cosmic epochs. And so, as we gently drift towards sleep, let us carry this tranquil awareness that our consciousness, our capacity to ponder these grand cosmic questions, is a rare and precious phenomenon, a temporary island of order and complexity in an endlessly unfolding entropic universe. The edge of the observable universe, then, is not merely a boundary, but a profound reminder of the fleeting beauty of existence, the delicate balance of forces that allow for our very being, and the enduring wonder of a cosmos that, even in its ultimate silence, continues to inspire awe. We are privileged witnesses to a dynamic, living universe, and in understanding its limits, we deepen our appreciation for the profound significance of our own transient yet meaningful place within its magnificent story. May these deep thoughts about the universe's grand journey and its gentle fading carry you into a world of tranquil sleep. Remember that the universe is amazing, and you are a part of it. Fall asleep with this feeling of serenity and endless knowledge. Good night. Our journey through the universe's fading beauty and the profound implications of its informational horizons brings us now to perhaps the most elusive and fundamental concept of all: time itself. If the cosmos is indeed destined for a state of ultimate thermodynamic equilibrium, a cold, dark expanse where all energy is uniformly dispersed, then what becomes of time in such a universe? We experience time as an undeniable, linear progression, a ceaseless flow from past to present to future, a rhythm that governs every beat of our hearts and every thought in our minds. Yet, physics reveals a more intricate and at times more unsettling picture. The very directionality of time, its perceived arrow, is intimately linked to the concept of entropy, the increasing disorder that defines the universe's evolution. It is the increase of entropy that gives time its macroscopic direction, allowing us to distinguish a broken glass from a whole one, or a growing star from its eventual cold remnant. Without this ceaseless drive towards greater disorder, the distinction between past and future would, in a fundamental sense, cease to exist, dissolving into an eternal, unchanging present. In a universe headed towards heat death, where all matter has decayed, all black holes have evaporated, and all energy is spread thinly and evenly, there would be no discernible events, no processes that mark the passage of moments. Imagine a vast, silent ocean, perfectly still, without a single ripple or current to indicate movement. In such a state, the very notion of before and after loses its cosmic meaning. Time, as an objective, universal clock, would effectively stop ticking. This perspective aligns with certain interpretations of Einstein's theory of general relativity, which views space-time as a four-dimensional block where all moments, past, present, and future, coexist. From this block universe perspective, time does not flow. Rather, we experience a subjective journey through its pre-existing landscape. If the universe reaches an endpoint of absolute equilibrium, it might represent a kind of ultimate, unchanging coordinate within this block. A cosmic stillness where the concept of progression no longer applies. This profound stillness, while challenging to our intuitive grasp of ceaseless change, offers a tranquil, if distant, vision of ultimate cosmic rest, a cessation of all dynamic processes. While the heat death remains the most likely long-term fate based on current data, cosmological models have, at times, entertained other dramatic possibilities for the universe's ultimate end, each with its own unique implications for time. There is the Big Crunch, a theoretical scenario where the expansion of the universe eventually reverses, and all matter collapses back in on itself, potentially leading to a singularity, a point where space-time itself might cease to exist. In such a scenario, time could theoretically reverse its arrow as the universe contracts, or simply end in a final cataclysmic moment. Then there is the Big Rip, a more violent end, as we touched upon, where the accelerating dark energy grows so strong that it not only tears galaxies apart, but eventually rips apart stars, planets, and even atoms themselves, ultimately shredding the very fabric of space-time. In this extreme vision, time might not just end, but its very coherence, its ability to define a sequence of events, could unravel into an incoherent chaos. Each of these theoretical endings, while vastly different in their cosmic mechanics, presents a unique challenge to our ingrained perception of time as an infinite, unyielding river, suggesting instead that it is a phenomenon with boundaries, conditions, and perhaps an ultimate cessation. It is here, in contemplating these grand cosmic endpoints, that our individual, subjective experience of time gains a renewed and profound significance. While the universe in its entirety might face a future where cosmic time loses its meaning, our own personal timelines are, for now, vibrant and active. Every second we live, every memory we form, every decision we make is carved out of this fleeting, dynamic epoch of the universe's history. We are living in a precious window of cosmic time where change is abundant, complexity is possible, and the arrow of time points clearly from past to future. This realization can evoke not anxiety, but a deep sense of tranquil gratitude for the unique and temporary gift of our conscious existence within this grand unfolding narrative. Our ability to perceive, to learn, to connect, and to ponder these profound questions about the universe's beginning and end makes our brief moments in cosmic time profoundly meaningful. We are the universe observing itself, reflecting upon its own journey, a rare and beautiful flicker of awareness amidst the vast, silent expanse of everything. And when we gaze at the night sky, this infinitude can evoke not a sense of